keep yelling blah 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 blah. And the word will spread fast here because it's a small town. A lot of people say here in Assiniboia, because they're going north to Moose Jaw, they say, oh, I'm going to go up to Moose Jaw. What do you mean up? Up is this way. Come in, please. And still you're going down in elevation from here to there. We're like 130 meters, 40, 50 meters higher than the town north of us. So again, you're going down to Moose Jaw, not up. Remember, I'm the uneducated one. I'm the stupid one, but yet I'm the only one who knows how to talk about directions on your supposed spinning ball and even on your flat plane that you live on. And if you think you live on a ball, you're going to have to tell me what direction east and west is. Is east down and west up? You need to figure that one out.
Okay, is anybody actually hearing me?
Because I'm sorry, I just, you've got to figure out what direction.
Okay. Mikey Smith's on one of his little crusades in his hometown. The reason why I started it is because he starts talking about evolution and big bangs, and it does. Like a lot of people, they don't get it. The Big Bang was just a rapid expansion of energy that eventually cooled down, and it took a lot of work to make society out of a Big Bang. But yeah, he's going around pestering people, especially at a construction site here in the Sabonia in southern Saskatchewan. Okay. And he goes on about how people use up and down as directions. Here's the thing, most of the time the map has the north on the top and the south on the bottom. That's why people say going up and going down. It's just the cultural thing. It doesn't have anything to do with elevation.
Direction you're going, and then you can talk about it, okay? I'm going up the stairs, I'm going up an escalator, I'm going up a hill. How many ups and downs do you have on your little world you live in? I'm going up north, but yet I'm going up a mountain at the same time. So you've got to pick one up and go with it, okay? So that really frustrates me, guys. Antarctica is not down, okay? It's the freaking highest landmass there is. So how are you going down when you're going high?
It's high compared to the ground, the average height of the ground, or sea level.
Higher. It's annoying. Freaking annoying.
Well,
when you're downshifting your car, do you go up? Then you're going to have to figure out what Flintstones is. Your parents did not explain to you what Flintstones was. You knew it was a cartoon. You were watching animated. It's not real, okay? I don't have to explain my sign to people because it states what it is. It's a cartoon. End of statement.
I think people can tell the difference between the Flintstones and reality, but for some reason he thinks space is a cartoon.
If they don't know what a cartoon is, I would highly recommend going to the hospital and getting checked out.
Like he should for his toe. And we actually do care about his health. It just he won't take his insulin or any medication for his diabetes.
Mommy, can I watch cartoons? Then your mom says, what's a cartoon? I do not need to explain my damn sign any more than it is. It says right there, computer generated image, or a fucking cartoon.
Or he uses his cell phone to take pictures and doesn't realize that that's a computer attached to the camera in his cell phone.
If you don't know what a cartoon is, I can't help you, man. What's with all the WRXs in town? What the hell?
Like if he had a channel just car spotting or train spotting or airplane spotting, he'd probably get more views and people wouldn't be making fun of him as much. But
very busy here on this street. Perfect. Absolutely wonderful.
okay, I'm going to need Mikey's with the window. I'm going to bring up another window here this morning. Okay, the Planetary Society did a in-depth article about how the spending for NASA is going down dramatically. Well, it's proposed. But this actually demonstrates the blue is, well, okay. The red is the proposed cuts in the next budget. And you can see NASA's going to get hit in the science and the space operations and the mission support and the environmental compliance and a couple other areas. The science, they're going to do drastic cuts to several programs. James Webb won't be affected. Hubble won't be affected, I don't think. But these are long-term projects. And the problem with cutting a lot of the long-term projects, even though a lot of them are, the satellites or the probes are no longer functioning, or is that there's a lot of data still in those areas, and you can see how far back some of these things go back. Terra, I had to look up some of these. I like Terra. It's a satellite that looks actually back to the Earth. It looks like the power supply was slowly dying anyway. So, looks like some people are viewing. Oops. I shouldn't be looking at that right now. So, I had to put my computer in a weird configuration for this monitor. So it's going to take me a while to flip through things. Oh, I was in the right window after all. But the thing is, cutting a lot of these programs is a lot of it. If there's still a lot of science to be done out of these projects, and plus a lot of them are long-term projects. So if you cut them now, you'd end up losing a lot of data and experience. So plus the environment. Some of this is thankful to Mr. Musk, because I think he's been having issues with the environmental compliance at his SpaceX launching facility. And like STEM is science, technology, engineering and mathematics, and that's more probably a public outreach. So if you don't get people interested in science or NASA or space, you're going to have a lot of problems in the future getting these people up. You can see this is since 1961, the budget. I know this is exciting stuff, but that's good. That's going to be harmful for a lot of space science. Let's see what Mikey's up to now.
Roger Ledwell, good to see you there. In something that's not generally said to be funny, you're sensing that it can and could be funny within that sentence. Like stating, I love farting in public. It's a funny statement, but it's a kind of a rude and disgusting statement because you fart in public all the time and you love it. But you're sensing the humor in that statement. I have a few friends that are just, they wouldn't even get it. They would not get it. You know, they take the average joke and laugh. Yeah. But they don't get the other statements or sarcasm that are funny, but you have to sense the humor. Right, guys? Oh, fuck. Am I really going to be in this person's way? Man, this is not a good place to park. I am so going to be in this person's way. I'll park right here again. Yeah, let's park here. This is better. I'm just trying to stay away from the noise. This way I can at least, I gotta be able to see my car. That's the thing. Everybody in town knows who I am. She wasn't bad. Farting is rude. I always fart on my balcony when I'm doing a show. Yeah, I got some interesting friends, you know, people that I know that are just, they're not here, all of them. They're kind of out to lunch a little bit. And again, you think we have 5 senses. Why? Because Google said we do? They even made a movie, The Sixth Sense. What about sense of humor, sense of direction?
There are actually more than 5 senses, but there's just 5 recognized senses. There's like balance would be another sense that people don't think of much, but but sense of humor is something completely different.
There's a lot more than 5 senses we have, okay? Don't accept the norm. Be abnormal. Be different. Be yourself. I'm different. I'm not even close to being normal.
No argument, but I'm not normal either, so.
I don't want to be normal. Normal's boring. I'm very different from everybody that I meet. I have the dark. I will over on Flatsoids by then. You watch Flatsoids? Interesting. I'd rather chew broken glass. He's not a true truther. I can tell you that much. And that's my opinion, and I'm allowed to have it.
You're allowed to have it, but we're allowed to contradict you, or whatever. Contradict you or point out where it's wrong.
We got truthers in the southern hemisphere, and they ain't doing shit for us. We should be recording things and comparing things, making observations.
Well, here's the thing. Hemisphere means half sphere. So, it's the southern half sphere.
But yet, they don't want to take part.
Oh, Mikey for a bit. So I want to talk about some other stuff. Okay. Okay. I think there's been a little over-concentration on flat Earth. Demystifying sci is... let's take a look. These are their conferences. These two people actually have PhDs, I think from Columbia, the two hosts here. But they pretty much sponsor a lot of the anti-science stuff. Okay, where do I get the podcasts? They actually do a lot of... No, it's right there. Sorry. They host a lot of the crackpot theories. But they have more episodes than this. No, they had one with Fraser Kane, but I think it was taken out. Okay. Just to give you an idea how many different theories there are. They do a lot of repeat guests, such as Dr. Robitaille. Okay. I'm going to go to one that I've actually already watched. It's over 2 hours long. I may have to skip over some stuff. Before we get started, Robitaille is actually a chemist or a solid-state physicist. He did a lot of MRI work, and so he's not a I don't know how quick to put it, but I'd start watching it.
Gaseous plasma. But it turns out that when you start digging into what we see when we look at the sun, when you explore its spectrum, when you see that it's a continuous spectrum that is an absolutely perfect black body, which only comes from condensed matter.
Okay, Kirchhoff's first law is that any opaque body, when warm enough, will be a continuous spectrum. It doesn't have to be condensed matter.
You suddenly start to realize that perhaps...
And condensed matter is solid or liquid, not gas.
Everything that we think about the sun, everything that we think about the stars, maybe even everything that we think about the Big Bang and the age of the universe and almost all of astrophysics and cosmology is not actually the right story.
Not only that, but if we don't understand how the stars work, then what are we doing trying to build little stars, in other words, fusion reactors, here on Earth? Well, it follows that we might want to rethink that process as well.
For the conversation, we have two of our absolutely most favorite people, and also people that we're proud to call mentors. We have Pierre-Marie Robitaille, who built the...
Okay, about fusion. We actually already do fusion on Earth. It's called an H-bomb. And these are done by taking fission bombs or uranium bombs and exploding them and collapsing hydrogen together. So they already happened. The problem that nuclear fusion power is trying to do is try to control it enough so they can get electricity out of it instead of just a big bang.
The world's first 8T MRI. And we also have Jim Keller, who has been a computer architect in Silicon Valley for more than 20 years. He has built at AMD, at Intel, at Tesla, at Apple. Now he's working on open source AI chips at Tenstorrent. He is also working on producing tabletop semiconductor fabrication devices so that companies can produce them in-house as easily as today. They can 3D print some component that they need for a machine. These two people are absolute intellectual giants of engineering and science, and today we brought them together for a conversation about the liquid sun, about the future of cosmology, about the differences between science and engineering, how to come up with incredible ideas, what it takes to build something great, and why incredible science is so hard to find.
And we investigate the death cult at the heart of modern cosmology and astrophysics. Jim is not only an incredible engineer, but he's also a great patron of the sciences, and Jim actually made it possible for us to begin planning this conference in Sesimbra this summer. And originally we had planned on having Pierre at the conference as well. Unfortunately, Pierre wasn't able to travel, so we figured, why not introduce them to each other and see what happens?
If you want to come to Sesimbra, Portugal, to Beyond the Big Bang and see the incredible slate of conversations that we have lined up with everybody from Gareth Samuel of See the Pattern, Alexander Unziker of Unziker's Real Physics, to C.S. Unikrishnan of India's LIGO project, including Eric Lerner, who kicked off this entire modern revival of the idea that the Big Bang never happened by publishing a book with the same name back in the 90s. It's an incredible weekend. We have only until June 1st for anybody who wants to come and have dinners with us. So if you want to come to Portugal and you want to come to the dinners Thursday through Sunday, get your membership as soon as you can, because on June 1st, those sales close, and then you are on your own for meals. We'll hopefully see you there.
Remember, even if you can't make it to Portugal, the only way that we fund this project is through you guys, which means we work directly for you. So if you're already supporting the project, thank you. If you're not yet supporting the project, remember, you could give 75 cents a week and make sure that we can continue to put all of our time towards this and bring you guys more and more of what you already love. So check it out over at patreon.com. And
enjoy the conversation. It is a real one with two absolutely incredible minds, me and Shiloh moderating. And we hope to hear what you think about it down in the comments. We'll see you on the other side.
The scientific revolution starts now.
The Dymystifing podcast.
Let us see in the dark.
Why does it matter if we're wrong about the way that the sun works?
Why does it matter if we're wrong?
Yeah, like so it's not a gas, and it's liquid metallic hydrogen, and we've been wrong all these years. Like, does it change things substantively?
Yes, I think it does change a lot. I mean, obviously, what man is trying to do fusion now with the ITER project, for instance, in France. And, of course, that project will not pump a single electron into the grid. It's an experimental project, right? But, and they're trying to confine a plasma using magnets doing that. But I don't think the sun is operating that way at all. It's got a lattice, and the lattice is helping the electron, the nuclei to fuse as they're vibrating within the lattice. So the nuclei are already aligned, and they're already getting ready to fuse.
One thing Dr. Robitaille believes is that it's not a gas, it's a lattice of hydrogen atoms, and this is one of the central tenets of his theories.
You know, as they vibrate, and then eventually they just tunnel through and fuse. So it's a completely different setup. And so if we're going to have successful fusion on Earth, I think it's important that we do rethink the sun. But it's not.
Okay, I've watched enough of his videos. I'm going to say something here. A lot of people who come up with these theories don't like the Big Bang. They don't like black holes, and they don't like a lot of that stuff. That's why they rewrite a lot of physics to do something completely different to fit their model. And Robotai's been at this for a year. He has a channel called Sky Scholar. No, don't. At the end, he says recommend it. Don't recommend it. It's just not how we figured out how things work. We could be wrong about some small details or some parts of it, but in general, we have a pretty good idea how the stars are working.
Not only important for, economically for mankind, it could be very important, but I think our understanding of astronomy will dramatically change. And so if we study astronomy because, that it helps us to understand our place, or, to understand the universe better, well, if we've got it all wrong, it's not very good at understanding. So I think to understand that the stars are condensed matter, that has great implications, not only for the sun, other star types, what are white dwarfs really? Are they ultra dense? Are they not dense? So I've said that the white dwarf just has a different crystal structure. It's condensed matter, it has a different crystal structure, and that's why it's not as luminous. It's not because it's small, it's because it just can't emit as well. Just like a diamond and graphite both have about the same density, but they have a very different crystal structure. One of them, graphite, is a perfect absorber, or close to perfect, and the other one's transparent. So that's the same thing that's happening. Why is the luminosity of the dwarf low? It's because you have a different lattice. So it helps us understand, the different star types and our complete.
The reason why luminosity of a white dwarf is low is because it's a smaller star, and therefore has smaller surface area.
View of astronomy will change if the sun is condensed matter. That's why they say that the sun is the Rosetta Stone of astronomy, right? Mm-hmm. Once you understand the sun, it touches everything, all the other star types, and
I want to know why it matters to Jim too. Obviously, Jim's been attracted to these ideas, and I think
there's two funny ones. Like, one's a meta-narrative, which is my belief is most of modern science is wrong, either fundamentally or incrementally wrong. Like, you could have a measurement where your theory is pretty good, but you're not accurate enough, for example, or you could have a theory that's just plain wrong. And the sun is really interesting because it's relatively close by. It flared, the Carrington event in 1859, I think it is, melted wires in the telegraph system. And it wasn't a particularly big solar flare. Like, they get 100 times bigger, right? And so there's, like, again, when science is wrong and lots of people are working on wrong theories, it's kind of a waste of effort, and science has been wrong about, like, everything. Like, the Ptolemy theory of, the solar system went on for thousands of years, and many, many physicists became trained in that. They did really great calculations, actually, which advanced some kinds of mathematics. But it was kind of a wild thing to think of all the senior physicists who studied the solar system for 1,000 years in universities were studying a fundamentally wrong thing. Now imagine if they had a better theory, right? They could have made more advancements, because the problem with wrong theories is while you can refine them and curve fit them better, it's not as expansive as a good theory that's better match.
Also, back then they didn't have the instruments that we have nowadays, and they never had satellites which were actually in space measuring things, and like the Parker Solar Probe that goes inside the atmosphere of the sun. So we've got better technology to study things now than we did in the past.
And the other thing is, if we don't understand the sun, it will be really a drag, for a big solar flare to knock out society. And the probability of understanding the sun properly with a wrong theory seems low, right? And now whether we can do something about it, who knows? I'm a fan of, if you have a real problem, some substantial number of people should be working on it. And
At least
I
we
don't
can
think you
expect
can solve that kind of problem or predict what the sun is doing if your theory is fairly wrong.
So before we get deeper into the question of specific aspects of the sun, I wonder if we could take some time to talk about the link between science and engineering. Because both of you are engineers.
Oh.
No,
Deep-
I'm a chemist by training.
That's true, but you built...
I assembled an AT, but yeah. I mean, I have great respect for engineers, and I did a lot of engineering, that's true. And when I was a person that didn't want to just be in the lab theoretically. I mean, I was in the laboratory when the AT was assembled. I was part of every step of assembling it. I was always in the laboratory. I was not at my desk and tried to guide every step. And so in that sense, I guess you could say I'm an engineer because I actually, use oscilloscopes and network analyzers and all the things you use in MRI. So, yeah, so in that sense, I have respect for engineering. That's for sure.
And I would say I have respect for scientists.
So, that's a good starting point.
And since we've just talked for many hours the last day or so, Pierre is definitely a scientist. He has a talent for engineering. So in the course of his investigations in the MRI, he figured out a bunch of stuff and then learned enough engineering to help build a machine. I'm an engineer. Like, I was putting things together as a little kid. And in college, I did well in math and science. But like, compared to real mathematicians, I didn't know anything. Compared to real physicists, I didn't know anything. I'm an electrical engineer. My instinct is always to make something. Like, I love programming because I could think about an idea and see it and program and then watch it work. Like, it's not that fundamental. Like, computer science is awkwardly very simple. We just count to 1 over and over. 0, 1, it's binary. So it's not deep science technically. There's a phenomena of, we were talking about this, of the complexity of modern computer designs is really high. And to successfully build a computer, you have to partition the problem and also partition the team and, build proper abstraction layers. These are engineering solutions to like a complicated task, to achieve a known goal. Like anomalies are interesting, but if we don't have to deal with it, we just walk right past it.
Oh, that's so interesting, because breaking down complex problems into these small teams for science is sometimes a disaster, because you get these teams working in isolation from one another and they don't have a wider view of the big picture.
Yeah, so in an engineering project, like 10 Story right now is over 800 people. It's technically 100 teams, right? And then they coordinate. And at various points, the teams coordinate together. And since we're making something useful, like software that works, or a chip that functions, or a business plan that operates, or a supply chain that coordinates with an engineering release date, we're constantly bringing the pieces together in, like, say, a falsifiable event. Like, it's going to work or not. And we know it all the time. So in a good organization, people own things with some clarity so they can do them. But they also, I joke that it's all input, function, output, right? And those things have to solve properly. And big companies where, say, they make too much money for a while, or they have a captured customer, they can do engineering projects that essentially have no falsifiable endpoints. And then those things go off track.
Anything?
What's that?
Like, they just never deliver anything?
Oh, some big companies, they make a new product every year, and the people need the product. So the engineering teams are engineering features and all kinds of things that nobody actually cares about, but nobody notices.
Interesting.
Like, does anybody care which iPhone they have anymore? Nobody cares. They make a new one every year.
Yeah.
I don't know which year my iPhone is. It used to matter a lot. Every new iPhone was a big step. Now, iPhone 14, 15, 16. For most people, they're the same. Like, there's some spec that changes. Apple will tell you it's 2x better, but nobody cares. So that's become like a not falsifiable output.
Okay, and so in the process of going to the lengths of engineering something, it seems like the difference between science is that it is exploratory and engineering is product focused.
Goal-oriented.
Okay, and so is there a place...
There's also this element of the meta-narrative that Jim mentioned, perhaps incidentally. The science does guide the meta-narratives that we use as civilization. And for me, and I'd be curious to Pierre to weigh in on this, the meta-narrative of cosmology and astrophysics is very bleak right now. Right. Dark matter, dark energy, black holes, like, it has this kind of...
The heat death of the universe.
It has a very deathful feel to it.
That's right.
which seems like it shouldn't matter that much, but it also is kind of like a flag we're waving as the civilization, right?
It's something that actually bothered me about the Vatican Observatory. I've never talked about this before, but of course, after Galileo, the church decided to invest in astronomy. And there was a very famous astronomer, Angelo Secchi. He wrote a book, Le Soleil, in French. And even if you can't read French, if you get a copy of the Soleil, you can get it at a university library. Just look at the illustrations of what Secchi had drawn about the sunspots on the sunspots and the characteristics of the sun. It's unbelievable. But Secchi was a great astronomer. But since then, what has happened, and I've met people that worked for the Vatican Observatory, and because of Lemaitre, who was a Jesuit, I don't think he was officially associated with the Vatican Observatory. I think he was at the University of Louvain in Belgium.
This is the father of the Big Bang.
The father of the Big Bang was an astronomer. And he was a Jesuit priest. And of course, they had this link of, okay, well, God, pointed at the universe, basically. I mean, it fit into the creation narrative of the church and actually, I think it was Pius the 12th. He loved it so much, he was going to use papal authority to say the Big Bang was real.
The thing is there's also experimental or observational evidence of the Big Bang, and Hubble found this by the further away, the more light is redshifted. He did this by observing Cepheid variables, and if you know how you can, they change brightness over time. There's a period to it. If you know how long it was between shifting between peaks in brightness, you could figure out how what their brightness was. Sorry for that awkward way of explaining it. Plus, there was also supernova, and they are not in a supernova. Well, nova are like white dwarf stars that are orbiting larger stars, and the matter compacts on them, and there's a sudden release in energy when they get enough. Their gravity can't hold in, but they produce enough energy for it to expand. And these two were verified. Plus, there's actually more ways now. They have another way would be asynchrotic. What is it? Red branch. It's basically super large red stars. They get bright. There's a certain point where they get bright, and they know exactly what the magnitude of the light coming from the stars is at that point. So they compare that to the Cepheid variables and the white dwarfs, and there's other ways. So they have more than one way of determining how far away these objects are.
Like he loved the theory so much, and finally the cardinals around him said, well, you can't do that. That's beyond papal authority. This is a question of science. But what has happened is that this love of this idea of God like pointing to a spot, and then there was a primordial atom, and it exploded and made the Big Bang, and people in the church loved it. But I always thought it was presumption. We will never know how the universe was made. That is just presumption. And then people think, well, Pierre, you're unscientific by saying that. No, I'm realistic of what is the potential of the human mind. You can have all kinds of ideas, but what is your probability that you're going to be ever correct, or that we can understand how all of this came about? We can look at it, try to analyze it, but my personal opinion is we will never really know. And one of the problems with the Vatican Observatory, and I think it's a little bit harsh to say this, especially as a Catholic, to speak against the Jesuits, but they've embraced this darkness. And that's what Shiloh was referring to, that we live in a dark universe. It's 95% dark matter and dark energy.
Dark matter and dark energy doesn't mean it's dark. It's just we can't observe it. So it doesn't mean it's black or that and absorbs light. It's just we can't observe it. And black holes is because light doesn't escape. Okay, we'll give them that's dark, but it has nothing to do with human psychology.
And I just can't understand why a priest would want to live in a dark universe. So I'm just telling you that this darkness, that we live in a universe of darkness. And, that has philosophical consequences. I think it has spiritual consequences. So, I mean, people will say, well, gosh, Pierre's a religious nut. He thinks that, this has got all religious overtones. But people don't say that about the Jesuits. That when they're happy with their theory of the Big Bang, they are willing to say, oh, well, they're not religious nuts. We accept all that. So I'm against it. I think philosophically it's quite wrong. And I think mankind needs to move away from it. And I think it will when they lose the microwave background, they will move away from the Big Bang. Finally, it'll be over.
Yeah. So
also, he doesn't think that the microwave background radiation is actually from the Big Bang. He thinks it's water. He thinks that the original Big Bang, the original background radiation observation was because the radio telescope, it was in New Jersey, Pizance and Wilson, observed the microwave background radiation, and he thinks it's light reflected off water into the radio telescope that they were using, and he believes that the Kobe and WMAP observations were also water from Earth, even though they were in orbit. So that's, he has an entire video, a 3-part video series just on the cosmic background radiation maps.
So on the darkness thing, so humans are animals, and animals are generally zero-sum game evolved. So the game theory we operate in is, if you're in a forest and there's a limited amount of food, if I eat, you don't, right? And in certain times of human culture, there's big optimism. Like post World War II, there was a huge technological expansion, and people were actually quite optimistic in the 70s and 80s and 90s. And then it sort of started to plateau there. But our default thing is we're running out of stuff. And I have people say there's no place to build. And I always ask them, have you been in an airplane? 99%. Like in Silicon Valley, everybody knows they're out of land. It's all locked up in conservation areas, and it's nice to have those. But if you look at the state of California, it's huge. Like another 100,000 acres to build condos would be fine, and nobody would notice it from space. So we have this I think intrinsic narrative about zero-sum game behavior, which manifests in kind of a weird negativity, as opposed to like an optimist thing, which is we live in a bountiful planet with lots of atoms, unbelievable amounts of energy, lots of people. I'm a big fan of lots of people who should be ideally doing the most thinking and the most fun things and interesting things possible. And most people's narrative is we're running out of stuff. And it manifests like peak oil. We're going to run out of energy. Well, we're going to run out of sunlight. Like the sun is amazing. It's such an energetic thing. And the same with the universe. The universe is clearly self-organizing. Like you can see there's structures now 1 billion light years across, right? And there's galaxies and threads of galaxies, and like it's so amazing, and it's bright and full of energy. Like the universe is very energetic.
I wonder if it doesn't reflect the climate of increasing scarcity inside the academic communities that are repairing the decree.
Yeah, and that's so interesting because the funding for universities is going way up. It's all going into bureaucracy. So the bureaucrats then decide, what should we squeeze? The bureaucrats? No, we never squeeze those, right? And the bureaucrats say they're delivering all these services, so all the professors are getting squeezed. Right. And part of it is, but of course you're getting squeezed, we're running out of everything. And that's pervasive everywhere. And why would we be running out of everything? Humans are unbelievably productive. And you only run out of things if something is diverting those things to some useless course, like maybe bad science, bureaucratic endeavors, corruption,
Well, science that's been chewed on is safe science as far as graphs are concerned, right? You want to add another significant digit to this measurement or another energy level of particle.
I like that.
But this links me back to the original question which set us on this path, which is, what is the line between science and engineering? Because I think that's not always clear. Because we've talked to Jim, to you a ton about the fact that, yes, there's theories for electromagnetic radiation and Maxwell's laws and like all of these things that are really, really functional. But then when you scratch at the surface of it, you end up at quantum mechanics that is not really explicatory. And so it seems like we're capable of building and doing tons of engineering without having a scientific foundation for...
Okay. About building everywhere, I'm not going to say that's them. Universities, there is probably room to be cut in the bureaucratic side of things. Part of the problem with universities is, the way I see it, is they got into a bit of a trap. They needed to get more students to get into the university, so they had to build bigger facilities and to get like football fields and stuff like that. It's fine to have football fields. Some universities went a little overboard, especially down in the States, and they have to get more and more students in to pay for those. But the line between engineering is more the application of science, and science is discovering new things. Yeah, on the quantum mechanics level, there's still a lot of stuff to be figured out on how things run or operate, and one area is string theory, and there's a bunch of different ways people are going into that and trying to figure out how things work on a quantum mechanical systems.
Those concepts. And so where does it become
We're going to
necessary?
have zero legit scientific foundations for anything.
Do you think it's that bad? Like,
Yeah. We don't know either space or time or gravity or matter or particle or fields. Like anyone that's really solid. Like there's theories. But and I really liked your guest, the shadow science guy.
Adam K.
Right, because he walked through about
Okay, just theories. Theories are okay. There's the there's the way everybody in society sees the word theory, and that means a guess But in science, it's a set of laws or a set of laws or rules of how things work. So there's quite a difference there. So it's just a theory. That's what a lot of people dismiss science as, just a theory.
how numerous times you weren't allowed. Like Newton was asked, he came up with the equation for gravity. He said, what causes gravity? He said, we can't know. Right now, Einstein thinks he came up with a solution. The same with heat. It's like, is it a fluid or vibration? We can't know. Right? Pierre, you just said it's possible, or you think humans won't be able to describe, how the universe came about. I actually think all questions where you say we can't know are probably wrong. Right? Like what causes electromagnetic field? Why is spin so weird? Like there's equations that sort of describe it, but they all math is infinite. Math is beautiful, right? And if you have enough data points, you can come up with math and curve fit to anything, and then you can say the math predicts spin.
But the problem
you would have never predicted spin from mass in general. Right, it's all guided by some observation. So,
well, it's interesting because you can say that it predicts spin because you have parameterized it sufficiently on the basis of observations, but the theory does not, in and of itself, provide for the necessity of spin as a feature.
So, in principle, a good theory is you have some data, you make a theory. The Kuhnian theory of science, or Karl Popper's theory is you get some data, you make a theory about it, and then it makes additional predictions.
Right.
And if they're right, you're happy. I don't believe modern science makes many predictions, but it makes a lot of curve fitting.
Right, a lot of patchwork.
Yeah, like the James Webb Telescope has all the astrophysicists off patching up all their equations because, every generation there's a new telescope. My joke about this is the universe used to be 3 billion years old, and then 6 to 7, and then 12 to 13, and the universe is basically 500 million years older than the best telescope can see. So when James Webb saw further, like I'm predicting that the new age of the universe will be 27 billion years old.
And that's part of the problem of why I said we'll never know. Because as our telescopes ever get better, we keep looking further, and then we keep discovering that the universe is ever so much greater.
Yes.
So how could you solve this problem? Do we live in an infinite universe? Is it finite? These are fundamental questions that mankind's unable to answer. We will never know the answer. Is it finite or infinite?
Well, I'll take a bet on that.
You'll take a bet?
All right. I think all questions describe where the answer is. You can't know. There's something we should work on.
Yeah.
It's like quantum mechanics. It's like you can't know this, and it's like, we couldn't know heat, we couldn't know gravity, there's a whole bunch of things we couldn't know.
Yeah.
Now the reason the reason that I differ a little bit. Now, first of all, the point I wanted to make was, when we talked about darkness, I never made the point that everything is light. We actually live in a universe of light. All the astronomers are monitoring signal that is coming to them as electromagnetic radiation at whatever frequency. It's not always in the optical. But we live in a universe of light. Yet our theory is now 95% dark matter and dark energy. This is crazy. Now, why do I differ from Jim a little bit? It's not that I don't want people to think about these problems. They can. Everybody is welcome to invest where they want to put.
The thing with the James Webb Telescope is they found galaxies that were formed a lot sooner after the Big Bang than they should have. But there's always a leeway in theories of there could be ones that are younger or older for a bit. So it wasn't really that big of a problem, but it got caught in the media as scientists don't know this or that about the age of the universe.
Put their life's work in. But in terms of how we expend dollars, that's a different problem. So when we had the Horizon well problem in the Caribbean, you remember a few years ago, right? We couldn't go plug the well. So mankind wants to do all these very great adventures, and we can't even understand our own planet properly. So I want to see things that, there's starvation on Earth. I want to solve local problems. And I think it's very dangerous to dream too. It's okay to dream, but you can't make everybody dreamers. I mean, you have to solve real problems on Earth. There are people that are dying on this planet, and that's a reality, and that's why I have a very conservative view on these things. When you see starvation, you cannot ignore it, and we do as a society because we're putting our money in these grandiose ventures. And so I guess that's almost unscientific.
This is kind of a false dichotomy. They think that that you have to choose one or the other. You can do both. You can actually build these giant build the telescopes and help humanity. It depends on where you want to put your priorities.
scientific to speak that way as a scientist, but it's a reality of the human condition. We have neighbors and we have to think about them. We can't just be thinking about our ideas.
But this is where the size of the check is inversely proportional to success. So like most of the great scientists of the 1800s and early 1900s, were underfunded.
Right.
Or independently wealthy.
Or had a patron or something.
Or like counts or lords or landed gentry.
I have friends who are well traveled in Africa where there is starvation, and when the UN and US government goes in with big checks,
I know nothing happens.
The local chiefs get new vans,
right,
trucks. Right, and all like the big water projects and sewer projects in Africa funded by big money fail because the big project doesn't have sufficient resources to actually manage it. Where meanwhile, local development, like in Kenya, I've been to Kenya and I have some friends there. It's really great. Right. And almost all the really great things that are actually uplifting people are underfunded local efforts and that. So my magic wand would be to eliminate big dollars. If your science costs more than $1 million, you're probably wrong, and it's probably never going anywhere.
What about?
That's okay. For some of the big for the big telescopes and big particle colliders, you do need money. But comparing that to how things work in the business world or in society is kind of wrong. Because, as you said, like the local chief would take most of the money, or one of the organizers would take most of the money, and that's not exactly comparable to the big science projects.
About like large scale detectors, because
$1 million, by the way, I want to say is not too much in science. I have to tell you that back when I was doing heart research, I mean, everything has become so expensive. I mean, $1 million grant today would be considered small in the medical circles, and it's unfortunate, but it's a reality. So.
Well, maybe it's like, what's the budget per person? Like the big particle colliders, they suck up billions of dollars, and lots of people focus on one narrow goal to prove a theory, which, who knows if it's true or not, and that really vacuums up a lot of attention. And I see this in computer design. Like, I used to have this graph where the time to do a project was inversely proportional to the number of people. So 100 people could build a computer in 2 years, 200 3 years, 400 in 4 years, and 500 people could never finish a project. And then Intel had a team of 800 people, and they finished the project. Not very good. And what happened is several hundred people doing the actual work detached from the organizational superstructure, and they finished the project despite the management team, which was really great. Wow. And I know because I hired half a dozen engineers from that project into a startup. And one guy was describing the thing he did, and he said, "What do you think?" And I said, "I'm amazed." And he goes, "Why?" He goes, "Well, it's completely unnecessary. Like, there's a way easier way to do this." And he goes, "I thought so. But you made it work. I think you're a genius. Like, I hired him. You did great work." So the problem with size is humans, in large masses, absent some really strong, organizing principle, inherently waste money. Right? Fail to solve things like starvation and health issues.
Right. I'm not saying we're going to solve these problems with big groups and stuff, but I think we do have to focus on some of the problems that are here on Earth. I mean, I'm not advocating to spend fortunes in all these areas. I realize that when you give a lot of money to countries, I mean, my uncle used to bring Canadian grain to starving countries, and the grain would just be offloaded from one ship to another and then sent and sold by that country so that the rich people in that country would get even more money. They wouldn't even give it to their people. There's all kinds of crazy things that happen in the world. So I understand that. I just think that astronomy has benefited from billions and billions of dollars, and a lot of it is for ideas that just don't make any sense. And the problem is they peer review themselves. So when they ask for their money, the friends are peer reviewing the papers or peer reviewing the grants and say, "Yeah, let's go for it. Let's give another few $1 billion on this effort." Yeah. And I think that society needs to say, "Hey, we need to calm it down on just permitting scientists to just spend money at will on things that aren't going to help humanity."
Okay, so this is actually.
So I'm a little tough on it, but
it gets back to the engineering question. So. Good engineering projects, there's a reason. Like, we need to build a bridge, it needs not to fall down, or my company's building a computer that competes with somebody else, and the marketplace will, somewhat decide which one is better, faster, cheaper, and having those endpoints. And then I make a joke about this. Like, there's, correct and incorrect in a 2x2, and falsifiable and not falsifiable. So as a scientist, correct and falsifiable is great. That's a testable theory. And incorrect and falsifiable, that's maybe you learned something, maybe you wasted a year of your life, and you found out your thing was wrong. Non-falsifiable becomes, buddy review. Like, people think this is correct and they think that's not correct, but it's not falsifiable. This creates a weird selection bias for non-falsifiable science. Because if you're going to do something and you're worried that it might be wrong, doing something that can't be proven wrong, good deal. It's a good. I mean, it's a funny thing. Right. But a lot of modern, physics and science and astrophysics is not falsifiable.
But isn't it because you have to start with some collection of things that are true and then build?
Well, we don't know how do we define true. I mean, if you look at the astronomers, they deny the surface of the sun. I mean, to me, that's unbelievable nowadays. I mean, how did the sun become a gas? Right? But in 1864, 59, I think Herbert Spencer first made the gas bubble. He had a bubble model of the sun, and it was gas inside and it has an outer bubble. And then she and Faye went with it, and then Lane finally in 1870, the sun kind of became a gas at that point. So, how did it become a gas? Well, and Faye writes famously in his paper that, he's looking at the sun and he decides that it's a gas. How did he know in 1864? And so it stayed in astronomy. We've denied the surface of the sun to this day. And to me, it's incredible. At every frequency, it's not only in the optical. I mean, they tell us the surface of the sun is an optical illusion. It's not an optical illusion. We see it at every frequency, from the sub-audio all the way to the gamma. We see evidence of a surface of the sun, yet they still deny it. So if we can't even get that right, And then they try to, it's an interesting thing about astronomers. They share to the world their discoveries, and yet they're unable to take any criticism at all when somebody says, no, this cannot be right. There is a problem here. And so this again goes to, they review themselves, and then they keep promoting the idea that.
Here's the thing. We don't think the surface of the sun is an illusion. What it is optically deep. It means that there's so much material stacked up that you can't see to the other side. So that's what I mean. It's not an illusion. There are different densities in the sun. Like the further down, the more dense you get. But people have done numerous computer models and calculations and stuff to find out how the sun works, and observations. So there's a combination of the two. So I don't think he understands what people are saying, but we'll let him go.
That the sun doesn't have a surface. And I think if I take you to a lake and I say, well, do you need to know what the lake is made of for you to know that that is a surface? It has a surface. Why does the public not call them on it and say, hey, the sun has a surface. Enough is enough. It's condensed matter. It's over.
We should at least be consistent and say that lakes are optical illusions.
Yeah, that'd be better. Or like Wikipedia's funny because there's a phase diagram of hydrogen, which is easy to look up. And it turns out when you look up a lot of them, you find out there's lots of variations because most of the phases have never been reproduced. They're theoretical, but let's imagine it has a diagram. The description of Jupiter and Saturn say it's obvious as you go down through the gas ball, the pressure goes up, and according to the phase diagram, it transitions to liquid hydrogen and then liquid metallic hydrogen, then to solid, right? But on the sun, that's not allowed to happen for reasons. And they're both of them are published in Wikipedia. So, like, they're both hydrogen balls. They're just one's bigger than the other, as best I can tell.
The metastability is a really important.
The thing is, the sun is a lot larger, so there's a lot more pressure in the center, and there's a lot more chances of creating nuclear fusion. Plus, for metallic hydrogen to exist, I think it's like 10 million atmospheres of pressure has to be. So it's a lot. So that's why it's inside the Jupiter and Saturn and not at the surface of the sun.
Piece of that puzzle when I discuss this with people as well, because if you try to map the phase diagram onto the surface of the sun, it doesn't quite work out, right? And so you have to bring in this idea of
Alexander Unzicker did the calculation about, according to the published phase diagrams, where it happens.
Yeah.
But that assumes that the atmosphere of the sun actually gets quite dense, and then it goes from transparent molecular hydrogen to liquid hydrogen, which is not transparent. But he published that in a book called The Liquid Sun, I think, based on Pierre's work.
So
I don't think he said there was a big problem with the phase
I think the pressure necessary to form the liquid metallic hydrogen should be a bit deeper than the surface of the sun.
It should be formed in the interior and then rise to the surface.
Kind of bubbles up.
So it's like a diamond. So it's like a diamond, right? We make a diamond in the interior of the sun, of the Earth, and then the diamond that comes up and it's stable, so it's metastable, but it takes high pressures and temperatures to make the diamond.
And diamonds will fall apart into graphene eventually.
Right.
And my prediction is the phase diagram's wrong.
So
as an engineer, I think, let's go measure everything. We can make probes that can get really close to the sun. We can do way better sensors. Like the sun's technically not that hot.
Don't you think that's hard to do for $1 million?
No, actually, we just designed a satellite this morning for $100,000. Here's the really wild thing. Again, so the world says going into space is really hard and complicated and expensive, and space is, somehow empty and simultaneously dangerous and a whole bunch of stuff. And SpaceX is firing rockets every week. Like, it's hilarious. And their cost goal is sub $1,000 per kilogram. So now getting something to the low Earth orbit is going to be relatively cheap. Now you need to make boosters to get out of orbit. But how much does a sensor cost? Nothing. It's a computer chip. Like, all sensors just detect electrons and electromagnetic waves. Like, they're not, there's inertial sensors. Like, the family of sensors is small. We could probably make a small sensor for everything we need to put it on the table. And it has to
Do you think we can touch the surface of the sun?
I don't know. It's
one of the things that we do know.
Or is it?
I mean, when I was a child, people told us about the gas giants, Jupiter and Saturn, and that they're gaseous. And I don't know, it was about 10 years ago the comet went and hit Jupiter, and it sure imploded on impact, right on the surface. It just exploded. So Jupiter is not just a gas giant.
The comet he's probably referring to was in 1994. So that's 31 years ago. It was comet Shoemaker leaving on. There could have been another comet since then, but yeah, that did hit the surface and did expose the underlayers of Jupiter to astronomers for a while.
Giant. I mean, it has a right density to be condensed matter. I mean, the problem with their idea is that these are gas giants or gas planets. Is their densities aren't right. The densities, the average density of the sun is 1.4 grams per centimeter cubed, and the gas giants,
which is like water, by the way.
Which is like water, and water is 1, and the gas giants are about 1. I think one of them is about 0.7, one of them is about 1. I can't remember exactly, but they're all about 1. These are gases, and so we just need to call them for what they are. I mean, it's enough of this stuff. I mean,
the thing is on the surface, it's very low density. And as the further you get down, it gets higher and higher density. So for a good part of Saturn or Jupiter's outer atmosphere, or even the sun's outer layers, it's not that high. But as you get closer and closer, it gets higher. So the average density is 1.41 or 1. And Saturn is, I think is the one he says is 0.7. And if you had if you could have a big enough ocean, you could probably float Saturn in an ocean. But if you were near liquid water anyway, you'd probably evaporate. Saturn would probably evaporate.
It's been 200 years. It's almost 200 years that we've been stuck in this paradigm of gaseous objects in astronomy.
So then
it's been what? We're 170 years into it. That might be enough now.
So walk us through the 100 grand satellite or the 100 grand probe to go measure the sun. Like, what does that actually look like?
We weren't measuring the sun. We were going to L2 to measure the microwave background.
Let's imagine we make a prototype satellite. So maybe it's a half a meter by a half meter, and inside it's a battery pack, a computer board, and some small array of sensors. So what do you want to measure on the sun? Temperature, pressure, electric field, magnetic field, gravitational field. All those sensors are small, like inertial sensors. Like every one of those things is small. And then the temperature, you can correct me, is reported to be 5,700 degrees, which isn't particularly hot. Now, most materials will melt at some point at that temperature. So you have a time frame. So you have to build a satellite with some way to cool it, and you have to go pretty fast. You're not going to land on the sun and sit there and do experiments. They landed a satellite supposedly on Venus, the Russians did, where it's 800 degrees and it operated for a while. So none of the components are expensive. Right, and you don't build the components mostly to withstand the high temperature. You build a heat shield to protect them from the high temperature. Right, so as you're going there, you want something very reflective, so it's not absorbing any energy, and you want to drive the satellite low, and you want to do a lot of small satellites. Like the weird thing about like the Hubble and the James Webb is they're amazingly accurate. Right, and they spent a lot of money doing it. Now the question is, someone company like SpaceX designed the next best, better James Webb.
Here's the thing: if they want to spend the money to send a probe to L2. There are a number of what are called Lagrange points, and these points are where gravity kind of balances, so you don't have to use a lot of energy to keep something there. I think L2 is on the other side of the sun. But every three-body system, like the Earth, the Sun, and a probe would have their own system. Another one would be for Jupiter. But yeah, go ahead. If you have the money and resources to do it, go ahead. Probably find out exactly what everybody else has found, but it's their money.
Telescope, I promise you, would cost $1 billion.
Sure.
The budget would be $1 million, and they'd spend $2.5 million, and it would be great.
Okay,
but our actual design was to go measure the microwave background at L2. We weren't talking about the sun. But interestingly, Dmitry Rabutsky, who was the first editor, who's the editor-in-chief of Progress in Physics, where a lot of my papers were initially published on the sun. And he had a dream of sending a probe just to go and pound the sun. Like all he wanted to do was look at this probe and design a probe that would go and hit the surface of the sun.
Oh, that'd be great.
And so no instruments. He just wants to send the ball.
You just have to throw a rocket to the sun.
So throw a rocket to the sun.
All right, so there's our prototype.
It would go in and melt and disappear. Progress in Physics, okay, I don't think is a very highly respected journal for what I've researched. There's something called an impact factor, which is the number of citations over the number of articles over the last 2 years, and the higher the number, the better the journal. I think that actually has a pretty low impact factor. I haven't looked at it lately, so that's one way of checking if a journal's a good journal. But if you throw something into the sun, it'll probably just melt and disappear. Which actually would, go ahead, do it.
So it needs to be big enough so it doesn't fully ablate on the way in. We need to propel it fast enough. We have the high enough resolution cameras to see pretty small objects at the surface. What's the current resolution of the?
I think it's not small enough now. I think it's still 10 kilometers or so.
All right, so we have to get a camera closer to the sun. Oh, so here's the thing. We send the rock, and behind it the camera makes, right? And so we stick.
So all right, see, there it is. An engineer has come up with a good answer.
Yeah. So you're saying the resolution is high enough. So then we go, this is just a camera problem. Yeah. Like how close does it have to be? And then what's the temperature profile look like? And then how do we make a camera big enough to be far enough behind the rock so we can see the sun?
So now let's talk about the temperature profile, because Jim wants to get his rock into the sun. So the astronomers are telling us,
sensors and everything else.
The astronomers are telling us that the corona is at millions of degrees, and it cannot be. The continuous spectrum, I was telling Jim yesterday.
Lean a little bit closer to this.
You're leaning out of the camera.
I was telling Jim today that the sun's continuous spectrum, the corona actually has a continuous spectrum, and it reddens away from the surface. That's been known for 100 some years, 130 years or so, that if you look at the continuous spectrum of the corona, not the E spectrum that is the line emission spectrum, but the continuous spectrum is showing reddening as you move away from the surface. So the corona is actually cooling away from the surface. It's not at millions of degrees. The reason that we see millions of degrees, or they interpreted it as millions of degrees, is the corona is electropositive, and any element like iron that touches this electropositive material will be stripped of its electrons, and then the electrons are channeled back down to the surface. So now you get iron 23, like highly ionized iron up in the corona, and they say, oh, well, the temperature's there. To make that in the laboratory, we need temperatures of millions of degrees. But that's not how it's made. It's made with a chemical reaction, so the temperatures are not. So this is another thing.
Can I throw in like a little anecdote that's kind of interesting? One of the early interviews we did on this channel was with Nikki Fox, who was the director of the Parker Solar Probe Project. And one of our first questions was something along the lines of, wow, if the corona is millions of degrees, how are you flying a spacecraft into that? And it was funny because it seemed to be a question she hadn't quite struggled with before. And so you could see her brain kind of working.
The thing is the corona is a very low density part of the sun, so you have to the particles in the sun actually have to hit the craft to give it that energy to warm up. So if you don't have that many particles per second heating the object, it's not going to do much to the object. Plus, they probably engineered it to dissipate the heat pretty fast. Yeah, Robitaille sees everything as a chemical reaction and not as a physical reaction, and that's kind of where he's limited to. I'm not saying he's stupid. He just doesn't have much exposure to this area of science.
It's out in real time where she was like, well, there's not that many of these particles, so if you left one particle in, a box and it's moving really, really fast, the temperature, technically average kinetic energy, is unbelievably high, but you're going to be very cold still if you encounter that collision. Right. And so the concept of temperature starts to, and this is something we've talked about.
I love the Wikipedia page on temperature, because you think temperature, when you grow up, is the thing you read on a thermometer. And then in chemistry science, you often put a thermometer in like a beaker of something, and you kind of have this idea. Then in physics, they start telling you it's vibrational, it's kinetic energy. If you get into quantum physics, and it's a population of states, and it's about electron orbitals, and you get to 0K, the atom stops moving, like so many things happen. And the Wikipedia page is epic because it's pages of temperature describing very different phenomena with many hyperlinks. And then, so temperature becomes but it's also super useful, just like energy is super useful, because energy also has many forms. And once you say joule, you think you can say A equal B equal C equal D, even though the phenomena are completely different. And it's sort of, as an engineer thinking, it's like useful to have a temperature. But sometimes, like I worked on a project where we had atoms at low pressure, and it was like, what does temperature mean? Like what happens to a gas when it's low enough pressure that it's not collisional, right? And the answer was, don't know. Like, essentially go do experiments to figure out what happens.
Well, this is part of the siloing phenomenon in science, right? You get these words that are very context dependent. I think plasma is another great example of that, where each scientist working in their own domain has a different connotation for that word, which is specific to their domain.
Right.
And then when they try to discuss between these tribes, people are talking past one another.
Also, they did an overgeneralization. So we're taught that there's, gas, liquid, solid, plasma. But the phase diagrams often have lots of states of these things. And then there's intermediate states, like a liquid metallic state and an ionized liquid metallic state. And it's sort of like, well, the simplistic version is sticky. Like temperature is sticky, energy is sticky, the four phases of matter is sticky. But the reality of matter is way more complicated and interesting. Right. But people will take a concept like temperature, apply it to the ionization state of an iron atom, and then declare the sun is 10 million degrees, when like it literally has nothing to do with anything.
The backwards problem, it might be worth just sharing with people, because this was a fascinating conversation we had last night about the temperature of the surface of the sun, which turns out to be the temperature of the rays from the sun, which may be...
Yes, that's what Planck said.
This is great. And this is
Max Planck warned the astronomers in his book, The Theory of Heat Radiation. In there's a section where he says that the spectrum of the sun that you measure, the black body spectrum, has to do with the temperature. It's characteristic of the rays. It has nothing to do with the real temperature of the surface. And that it's inappropriate to set the temperature of the sun this way. Planck actually warned them. Nobody paid attention to it. Now, why did Planck warn them?
Can you lay out a little bit more like what it means for the temperature of the ray rather than the temperature of the surface?
No, he says it's a property of the rays themselves. It's not a property of the surface.
The surface may have other heat.
Yeah, there's other
dissipation processes.
Yeah, I'll explain it to you. So Planck knew that to have a black body spectrum, there were certain conditions that had to be met. So you had no convection, no conduction. So when the astronomers are taking a temperature from the sun, they have to assume there's no convection on the sun. Well, is there convection on the sun? Obviously there is. It's quite visible that there's convection on the sun, both in the granules, as you have matter coming up from the interior of the sun and then rising to the surface. By the way, this is Baynard convection, which is a surface-driven process. That's one of the proofs that we have a real surface on the sun.
It's a bubbly-looking surface.
Yeah, it's a bubbly. Well, it looks like oil that you put in a pan, and then as you heat it, it makes this Baynard convection. And the astronomers have even referred to that as Baynard convection, but now they try to move away from it because they realize that Baynard convection is a surface-driven process, and they try to tell us that there's no surface on the sun. Now, relative to what Planck said is you can't have convection or conduction and get a valid temperature. Now, I've expanded on it. I said, why do we get a black body curve? What is happening? And I've linked it to the vibration of atoms.
There is convection. I don't know if it's Baynard's convection or not, but there is there is in the center of these granules, there is gas rising, and then it cools down, and then it sinks back down. That's how these granules are formed.
Of nuclei that are vibrating within the confines of a lattice. If you don't have a lattice, you'll never get a black body spectrum. That's why I've told people, whenever you have a black body spectrum, you have a lattice present somewhere. And so the atoms are vibrating, so the black body spectrum is produced by the vibration of atoms inside the lattice. But the lattice could also be moving. So what's happening in the sun is you have convection currents, and there's energy in those convection currents, right? So you get a certain amount you get a temperature which you could link to energy. So, E equals KT, that's a the energy is equal to Boltzmann's constant times the temperature. This is a well-known little expression in physics. And so if you know the temperature, then using Boltzmann's constant, then you know the energy involved in that system. So, but that is only the vibrational energy of the system. What I'm saying is you don't have equipartition in the sun. So when you have a gas, chemists talk about there's different modes of energy. Energy is distributed in different modes in the gas. You have translation, you have rotation, and you have vibration. Like if it's a diatomic gas, the atoms are vibrating, right? And then, but the dipole, the diatomic molecule can be rotating. There's energy in rotation. There's energy in translation. And there's a theory called the equipartition theory that, the energy must be equally distributed in this gas in all these different modes. In vibration, rotation, and translation, we have equal partition of energy, equipartition. But that doesn't happen in condensed matter. In condensed matter, there is no equipartition. So you can have a certain amount of energy in the vibrational mode, which is what we see in the sun. We're seeing the vibrational mode of the sun as the atoms are vibrating within the lattice of the sun. But then there's also convection currents. Now, how much energy is in the convection currents? We want to know that. And what I've said is, we can see it when you have a flare at the limb of the sun. When this occurs, we have gamma rays that are coming towards, or X-rays coming towards us from the limb of the sun. We see them. And the reason it's at the limb is that there's anisotropy there, that it's not emitting in all angles, but just preferentially in one angle. And at the limb, the angle is right so that it comes to the Earth and we see it. Okay. Now, why are we getting X-rays there?
Super high energy light.
Right. And so what's happening is that the flare is breaking out from the sun. Material is being ejected from the sun. It's pushing away from the sun, and material that's flowing on the surface comes and hits it. And when it strikes, that's like hitting a wall. It's like striking a wall, and now all the energy is transferred from translational into emission, and now we see the X-ray. So what does that tell us? That the energy equivalent of the convection currents is in the millions of degrees. And that's why in the New York Times article I had written, the surface of the sun is at millions of degrees, but it's all trapped in translation.
Okay, I'm going to admit one thing. I don't know the sun that well, so I don't know what he's... I don't think no, the surface of the sun is not millions of degrees. It's been measured at about 5,700 or 5,770. One person swears by 5,779. But it's in that range. So we know. So it is measured to a certain degree. So. And also, when he talks about how it gets redder at the edge, there's this is one of the proofs that it's actually a gas. Is that with fusion in the center is because the photons are created in the center of the sun, creating when the energy is created. It has what's called a random walk. It takes a while for the photon goes out, tries to go out. It gets hit. It hits a particle. It bounces around, and this does this for about 100,000 to 1,000,000 years. And when you're looking directly in the center, you're seeing ones that are just coming straight out. And when you're looking at the limb, you're looking at ones that have to bounce around and bounce at an angle towards you. And there's fewer of them, so that it looks darker or redder at the limbs.
It's trapped in translation. We only see the vibrational energy is what we see from the spectrum. So I don't think people understood it. They must have thought, well, Pierre's not. The surface of the sun cannot be at millions of degrees. But there was a reason why I said it, and that is the reason that we have energy that's trapped in convection currents, which we're not sampling. And then we also have energy in conduction. We have electrons, so we were talking about plasmas. I said the sun is a one-component plasma. You have a lattice where I'm talking a long time here. The lattice, we have...
You're not in a hurry, Pierre. It's totally fine.
I'm sorry.
No,
so you have a lattice, and the protons are...
Try not to tap the table quite so much.
Wonderful.
Pierre, finish your thought.
So you have a lattice, and the electrons, the protons are arranged in lattice points, and the electrons are free to flow through that lattice. And so the electrons are delocalized, and you have conduction pathways through this lattice. So in the metallic hydrogen model of the sun, you can actually have conductors and insulators. The intercalate zones are insulators, and you have conductors in the metallic hydrogen layer, the hexagonal planar layer. So it's much nicer because it can help you explain why do we have magnetic fields in the sun. You have to have conduction that's controlled, electron conduction or charge motion, in order to have this magnetic field. And how do you get that in a gaseous sun? You can't. So anyhow, what was your...
Well, so you use the word temperature for the energy of convection.
You can link it to a temperature.
You can link it, and that was confusing me before. But you imagine you have a ball, and inside you have somebody swinging a very heavy weight. Like the weight doesn't get hot, right? It's just, but it can have a lot of energy. So a simple thought experiment is you have an iron box that's hot, and it has some black body radiation spectrum, or maybe it's coated with soot. So you have black body, and then you have another box where inside it's actually not hot. There's a spinning weight, but occasionally it runs into something, which translates it to heat, which then can be put on the box. So the two boxes could have the same black body temperature, but one of them could have 100 times more energy in it because the convection holds energy in a really interesting way independent of temperature. It needs a method to translate the temperature, which I really like if there's a large amount of convection energy in the sun and then it hits something, you can sort of get a gauge of how much energy is in that by what the emission is.
And then you have the conductive energy too, which is kind of like what you would feel if you grabbed a live wire, I suppose.
Which you could also, you see the magnetic fields and you should be able to calculate this. So as an engineer, my brain goes to what sensors do we need, or do we already have enough data, and how do we start making the models to go figure this out? Because again, it would be useful to know how the sun works.
Which is a really interesting failure point of magnetohydrodynamics because it doesn't actually deal with the currents themselves on their face. It assumes the magnetic fields are baked into the system.
And this is, especially science that we've inherited, right? So when you, like I was taught Schrödinger's equation describes atoms, but we can only solve it for like a hydrogen. And maybe we can, maybe we can't. And then all science is at some point becomes statistical. right? And statistical or curve fit, right? And that's useful, but you have to know the boundaries of it, because as soon as you're outside the boundaries, now you're talking nonsense, right? And like the magnetic fields of the sun are clearly very dynamic, and things are it's wildly intense, especially in flaring times.
So that is a really interesting entry point to a lot of the crises in astrophysics and cosmology, which is the exceeding of these boundary conditions, right? The famous who's the gentleman who did the Schwarzschild solution to the field equations, which opens up the door to black holes, right? It's obviously exceeding the boundary conditions in theory for which it was designed, but all of the fun stuff happens when you go outside of physical reality and start to propose these exceptions that
which are all untestable.
Of course.
By the way, I think Steve will tell you that it wasn't Schwarzschild, but it was Hilbert that made the mistake. It's not a Schwarzschild solution, but astronomers keep assigning it to him. But anyhow, I'm not an expert in relativity. If Steve was here, he would speak right now. He's not here. He would defend, though.
I'm excited to say, though, that Steve will be coming by our house soon, and hopefully we can get to the
Get it straight from him. Yeah. That's right. He's a person of great moral fiber, Steve Crothers, and that's something that's been missed on a lot of the world community that attacks him so much. I mean, Steve is just an unbelievable person. He's got such integrity, and I think he's an extremely talented scientist. And someday I hope that people come to recognize everything he's done for science. He's been invited a couple times to Russia to relativity meetings and has spoken about relativity, of his points on relativity. So he's well known actually, and I think he can stand his own. There are some problems, and I think Steve has found some significant problems in relativity. But that's a side note.
He's the only person you've written papers with about these kind of things. That's what
I write with. I'm very careful about who I write with. I used to write with a lot of people. And now I have a very limited group of people that I write with. I've written with two of my sons, and I write with Steve. Steve is he's a wonderful colleague. I flew to Australia one time. I was working on Kirchhoff's law, and I had sent him a copy of Planck's book, or we discussed a copy of Planck's book. Then I had 2 copies at home, and then I flew to Australia to work with him, and we wrote a paper in 2 weeks together, which was kind of interesting. Planck had written a derivation of Kirchhoff's law in his book, The Theory of Heat Radiation, and Steve and I started talking about it over the phone, and all the problems in Planck's derivation of Kirchhoff's law, which nobody called him on. So Kirchhoff's law, for people who don't know, it says that within any opaque object, if you take an object that's opaque, that means light cannot get through its wall. Within that opaque object, if it's sitting at equilibrium, the radiation inside that object will always be the same, and it'll always depend only on temperature and frequency. And Kirchhoff actually never did any experiments to prove his law. He just did it mathematically. But his law is critical for Planck because it gave a universal nature to Planck's constants. So the Planck's constant and Boltzmann's constant, they gain a universal characteristic. That's later in the theory of heat radiation. So in Planck's book, if Kirchhoff's law is wrong, then we have no universality of these constants. And Planck had said that these constants will be measured even if you had an alien being in another planet far away, he would get Planck's constant. He will come to the same constant. And that is not true because Kirchhoff's law is false. And that's one of the reasons that, if Kirchhoff's law is correct, astronomers get to use Planck time, Planck length, all these characteristics that they use all the time in cosmology. They have a fundamental unit. That unit, nothing is going to be smaller than the Planck length if Kirchhoff is correct. If Kirchhoff is wrong, then those units have no more meaning than a meter has versus a yard. Okay, so it's a big problem for astronomy if Kirchhoff's law collapses. But the problem with Kirchhoff's law is it was done mathematically. It was a mathematical law. There was no experimental proof. And then Kirchhoff's own proof, his own mathematical proof, collapsed. So I think it was Hilbert in 1913 that said there's no valid theoretical proof of Kirchhoff's law anymore. So then Planck, in his book, The Theory of Heat Radiation, he tried to formulate a proof. And then Steve and we started talking about Planck's proof. There was so many problems with it. I flew to Australia and we wrote a paper on the proof of Kirchhoff's law by Max Planck. And I think the paper will stand up to the test of time. We did it right. And it shows that Planck's derivation of Kirchhoff's law is incorrect. And so there is no proof of Kirchhoff's law. Now, the beauty of working with Steve, we are very different people. I am an early bird person.
Okay, I'm going to look up Kirchhoff's law because what I'm familiar with Kirchhoff's is that if an opaque body is if an opaque body is warm enough, he'll give off a continuous emission. If there's a gas between the opaque emission and the observer, there will be an black lines, which will be an absorption of different energies, and you can have Kirchhoff's laws. Okay. There's the circuit laws. And it deals with electricity. The first law, Kirchhoff's junction rule, states that for any node in electrical circuit, the sum of the currents flowing into the node is equal to the sum of the currents flowing out of the node. And voltage law is the directed sum of potential differences voltages around any closed loop is 0. Okay. Well, yes, I'm using Wikipedia. Cross circuit law, thermal radiation. There's not much math to it. Okay. For a body of arbitrary material emitting and absorbing thermal electric waves in thermodynamic equilibrium, the ratio of the emissive power to its is absorption. Okay, I'm not good. The equilibrium. There's basically 3 parts of it. Is that a body warm enough or giving off light will be in a continuous spectrum. If you have one that's a gas between the body giving off light and it'll absorb light, and there's the emission, like if something's excited, it will give off specific lines of bright light, of light. So there's not much mathematics behind it. And I put the wrong window. So here we go, back to him.
I get up early and I start writing. Okay, and then but Steve is a night owl, so we basically worked around the clock. Like I would work
the handoff.
We hand off in the middle of the night. But it was such a pleasure to just be with Steve Crothers in Australia. Anybody who would get a chance to become friends with Steve would feel enormously privileged. He is just a wonderful guy. So that's my 2 cents.
Do you think there's conditions under which Kirchhoff's law is valid?
No, it never is. There are no conditions where it's valid. So if you look at opaque materials, one extreme would be a box lined with soot. That's probably a very good absorber as a natural absorber. There are better absorbers that have been synthesized than soot. And
this is like an ideal black body.
Yeah, so that'd be like if you'd have a cavity and it's lined with soot, and that would be an ideal black body. But if you take a perfect reflector like silver, and you make the box out of polished silver, well, now even Planck recognized in his book, in the Theory of Heat Radiation, he recognized that a perfect emitter, it has no emissivity. That's by definition, it's a reflector. So Planck wrote in his book that the radiation inside the perfect reflector will be undefined. But then he writes, but if we put a little piece of carbon inside...
Emissivity is the ability to absorb and give off light. There's a specific spectrum called a black body spectrum, which is an object, because a lot of objects are assumed to be black bodies. They're a perfect absorber and emitter of light. So a black body, there's so. I should let them talk.
It'll thermalize the radiation and it'll immediately accept the right form. Well, that was complete nonsense. I hate to use that word when I talk about Max Planck, because people have to get me right here. Planck's equation is correct. I don't have a problem with Planck's equation. I have a problem with Kirchhoff's law. But when Planck put the little piece of graphite or little piece of carbon inside his box, and by the way, in the heat radiation, in the theory of heat radiation, he's inserting little pieces of carbon everywhere. It's constant. I wrote a whole paper on it of all the times that Planck has used a little piece of carbon.
Well, so he's creating a boundary condition where he's saying that by including this, all of a sudden you have something that you can look at and then read off of it.
Well, the problem is that when he puts the little piece, if you put a perfect absorber inside a perfect reflector, what happens? You have a perfect absorber. That's as if you had lined the whole box with graphite. It's perfect. What is the definition of perfection, right? So once you put it in there, you build the soot box. That's why you get the right spectrum. So the graphite is the key. It's a perfect absorber. So any ray that comes in and hits it will be thermalized, and then you get the right black body spectrum. So the problem with Kirchhoff's law is it's like when you take calculus, you have limits. You have a limit on the left, you have a limit on the right. Well, one of Kirchhoff's limits is the black body lined with soot, and the other one is the perfect reflector. But the problem is that on that side, the limit is undefined. Even Planck knew that it was undefined because you have 0 over 0 in Kirchhoff's law. You have absorption over emission, and it's basically 0 over 0, which is undefined, and Planck knew it. It's so that the law doesn't work. It's not valid. You have between the undefined perfect reflector and the black body, in the middle you have gray bodies. And like he's an engineer, he knows that, and he's a communications engineer, or probably is aware of communication engineering a little bit, and he would know that, hey, we have microwave cavities everywhere. Our cell phones work because Kirchhoff's law does not work. If Kirchhoff was right, we wouldn't have cell towers. They wouldn't work because every one of these cavities that accepts the signal would be black inside. Right? How do you make the simplest black body? You take a block, let's say of iron, and you drill a hole in it. And that makes you a very simple black body. If you sample the whole, it'll be black inside. If it's a
Okay, the way I understand radio works is that the antenna, the wave comes in and it vibrates the electrons in the tower and creates an electrical signal. I don't know about these cavities inside the machine, inside of the receiver. But the thing is in nature there's no perfect reflector, because everything everything absorbs light and emits light, so there's some kind of black body or gray body. And scientists don't actually take the temperature they get from a black body radiation as the absolute known temperature. It's usually referred to as the effective temperature of the object. But if somebody knows about these cavities in the how cell phone towers work, put it in the comments if anybody actually watches this.
graphite block, it'll definitely be black. If it's a reflector, it will reflect whatever is outside. So anyhow, the reason that we have cell towers or that we have microwave communication is because Kirchhoff's law is false. And so it's
Can you draw that more explicitly for me? Like, why is the falseness of Kirchhoff's law?
Because the box would be filled with black radiation if Kirchhoff's law was right.
As opposed to
so the noise power would just be huge inside the cavity. And that's not what we're seeing.
It'd be like self-eliminating.
Yeah. So it's just like an MRI.
Okay. I can't remember the woman's, I think it's Anastasia or something like that. She's actually, sometimes she gets really skeptical when in these interviews, and she actually asks some really good questions. The other guy, I think it's Shiloh, sometimes just takes things.
Right? We build cavities in MRI, and this is what got me down this path of Kirchhoff, right? If Kirchhoff was right, perfect reflectors that we use in MRI they'd all be filled with black radiation, right? But they're not. Thankfully, they resonate. Inside a perfect reflector, you have standing waves, right? So when you have standing waves, you don't have a black body, which is, I'm talking too much, but that's what I was telling Jim yesterday. We were talking about the microwave reference load on the Planck satellites, and they have standing waves inside them. Well, if you have standing waves, that means we shouldn't have launched this satellite. The LFI was not working even when it was on the ground. It has standing waves within its reference loads, and that's published. I mean, I'm not just saying it. They are standing waves there. So black bodies don't sustain standing waves. So that's an important point. And so microwave technology would not exist if everything was thermalized inside a cavity. It's not.
And I think a consequence of the reality behind this invalidation is that emissivity tends to be ignored often when astronomers talk about Stefan Boltzmann relationship, things like this. I've noticed it in my own astronomy textbook. I teach astronomy at the university, that it's disappearing from the relationship. Like you'll often see this nice squiggly proportionality sign as opposed to an equal sign in the Stefan Boltzmann relationship, because they don't want to talk about the emissivity factor, which is really quite important as we start talking about strange stars like white dwarfs, neutron stars, right? It actually becomes the key player in interpreting those. But if you don't see it in the equation, then you start to think that it's not an important part of the puzzle. And then maybe
because for most bodies, it's not important. It's probably not important to take into a factor. That's probably why they don't put it in the formula.
It's nice to ignore it because of these contradictions as they mount.
Right. So Pierre, so you just alluded to something like a neutron star. And over time, they've made measurements and accumulated like assumptions, right? So somebody says, I have a theory about this, and they make an assumption, and then they try to prove it mathematically or observations, and then they sort of accept it, right? And then everybody's incrementally building on it, and the problem is like the weak chain of evidence gets there. The related theory, Unzicker talked about this, which he called subtractive science. And his example was in particle acceleration when they started. They shot a charged particle in a vapor chamber with a magnetic field, and you can measure the curve, and you get some idea about its mass and its charge interaction with the field, which sounds great. And then they started raising the energy of the beams, and then they started making colliders, and the problem was, to see the new thing, they had to subtract out the old thing. Right, so they start building sensors that sort of filter out, like essentially the noise or the stuff they already know, right? And then the problem is now they're co-designing their sensors with the result, right? And at some point they're subtracting out almost all the signal, right? And he said the Higgs boson, it was like 2 photons out of a billion that they were measuring, and then the sensor was literally designed to find exactly that photon, and then something stimulated, and they said, yes, I found it, right? Which became circular, and so that. And you said about the satellite calibration, it became circular. So there's this kind of, like the 3 pillars of error is like accumulated assumptions, which may be a little bit wrong or used out of context. Subtractive science.
The thing is, if you build a sensor, you'd probably know what the limits of the sensor are. And you'd be able to take out the stray signals. And if you know the other results of what's going on, you'd be able to easily take out that signal. So you can figure out what's left behind. There's an entire kind of analysis called Fourier analysis, which which does this. It's basically it uses like waves to figure out what to take out.
Science, where to see the phenomena you want, you have to design a better and better sensor. And as an engineer, that makes sense. Like if I'm looking for an X-ray photon, I'm not going to make a broad spectrum thing. But now I'm starting to look where the light's good, right? And these phenomena, and then the self-calibration of, well, these assumptions are correct and these assumptions are correct, and I calibrate it with some confidence and I make a measurement, but somewhere the chain got broken.
Right.
So you're familiar with the subtractive science problem? Yeah. So
actually, that's what happens in the WMAP satellite and the Planck satellite. Both of them are taking a difference of this. Well, Planck is taking a difference of the sky and a reference load, and WMAP is taking two regions of the sky, taking the difference.
Yeah. So, like at one point, can you say it goes wrong? Because like in particle physics, when they started subtracting out a little bit of signal to get clarity on the new phenomena, like they were all like, "This is great," but at some point the subtraction got so big that they're essentially just stimulating their sensors, and then between that and calibration, it's the probability of basically finding what you're looking for gets quite high.
Right.
And then, like, but where was the line? Like, how did
it start? Like when we talked about the white dwarf, why did the white dwarfs become ultra dense? And that's because of basically Eddington, that he knew that the luminosity of the dwarf was low, and so in order to account for the low luminosity of the dwarf, he all he had was Stefan's law, the Stefan-Boltzmann's law, and he had radius squared and temperature to the fourth. These were the only two terms he had.
This is one of Robitaille's go-to tactics, is that he'll use historical figures or historical papers to explain his theory, but the thing is our sensors have gotten better, so we actually know how things work. We can actually measure almost photons at a time, or we can know the energy that we receive over amount of time, so we actually can pinpoint the spectrum of a star or how much energy a star gives off. So we're not limited to just what Eddington reasoned about a century ago. Eddington was one of the best, one of the top astronomers about 100 years ago. I think it was Oxford or Cambridge, but he was he's one of the best. He was one of the top astronomers. He's one of the ones that proved Einstein's theory of relativity. He was kind of racist, British racist towards Chandrasekhar, who, well, they have a satellite named after him, and Chandrasekhar came up with the limits of where white dwarfs and neutron stars were while traveling to England. But it was the British kind of patronizing. They kind of do the same thing to the Americans at times, but.
He had the temperature, he could see the color of the dwarf, so he knew the temperature, at least the vibrational temperature, which we will correct here. So he couldn't touch that term. They dropped the emissivity term, which is Shiloh's point earlier, and so all that was left was the radius. So if the luminosity dropped on the left, so you got luminosity is equal to, I think it's 4 pi r epsilon r squared t to the fourth. And so the epsilon is gone. We assume that there's no emissivity, all the emissivities were 1. And so all that was left that you could change was r. So if the luminosity dropped, for Eddington said, we have to make the radius small. That's how we got a white dwarf. We made it small because we ignored epsilon, and so the only thing that Eddington could change was the radius. So then we made it small, we knew the weight, so we made it ultra dense, right? When you drop the radius, now all of a sudden they became ultra dense. And then they said, okay, well now let's look for a proof. Well, the gravitational redshift became the proof. So then when you start looking at the gravitational redshift, the only one that worked was the one for hydrogen. But the problem is there's quasi-hydrogen molecules on white dwarfs, and that will cause a redshift. So you can have a redshift that has nothing to do with gravitation. Then, if you look at all the metallic lines, if you look at all the hydrogen lines, let's say the hydrogen alpha line, beta, gamma, they all have different shifts on the dwarf. But if it was gravitational redshift, all the shifts have to be the same, and they're not. Then you look at the metallic lines on the dwarf, and they don't confirm the redshift of the hydrogen alpha line. Some of them are blue shifted, some of them are red shifted, depending on what metal you're looking at. So these are proofs that the white dwarf is simply not ultra dense. It came because Eddington threw away the emissivity, which was Shiloh's point. You cannot throw away the emissivity. You change the structure. Some of that might be due to the rotation of the star itself, but you'd have to do a deep dive into each line to figure out what's going on there. So what happens? Sorry, I'll tell you quick. So what happens is, you have a certain structure. This is the graphite versus diamond structure, right? I don't know what the structure is on the white dwarf, but I can tell you it's not hexagonal planar. Okay, somehow the structure has changed. The crystal structure of that star is different, and that's why its luminosity is low. It has nothing to do with density. Just like diamonds and graphite have essentially the same density. Same with the star, the sun, and the dwarf. The dwarf just has a different crystal structure. So this is a radically different way of reinterpreting the data, and it's high time that it happens. If the sun has a lattice, so does the dwarf. That means it has a different lattice. That's why its luminosity is low.
And I think that Jim's question about, at some point you have to correct for the noise of the observation. You have to start pulling things out, and you're pulling out so much that you're left with something that is a highly artificial picture of what's actually happening.
This was the assumption problem of, let's assume emissivity is constant. So now you have less variables to play with.
Right.
And then they were happy to say emissivity is constant, let's generate a radical new kind of matter.
Sure.
Right.
And that's part of that interaction with astrophysics, which is way out there, particle physics, who they like to bend stuff.
Yeah, the problem is...
I want to make a point. And I think the point is exactly what you said about the hydrogen is redshifted, other things are blue shifted. If you're going to be subtracting away things, in order to verify if you're actually looking at something real, I think you have to have multiple vantage points that all have to agree with each other in order for you to be able to say
so this is the cherry picking problem. Spectroscopy, every line means something.
Right.
And some of it's all under.
The problem is we are kind of limited to our vantage point, at least for now. But that's the problem. We only have one vantage point.
Should probably some of it's not but you can't ignore the stuff that's actually well understood.
So they tried to say, even the problem of looking only at the hydrogen alpha line. Okay, they say, oh yeah, we've measured the hydrogen alpha line on Sirius B, which is our closest white dwarf, and we know that redshift is exactly what Einstein would tell us it needs to be. Okay, but the problem is that the other hydrogen lines in the same spectra, they don't want to touch those because they don't give you the same redshifts.
Okay, what are you talking about redshifts? There are several different types of redshifts. There's a redshift due to the amount of dust between us and a star. Also, the gravity of the star will force light will slow light down, and it will be redshifted. So if a more massive star, the light would be redshifted down towards the star because the gravity's slowing it down. There's also galactic redshift because of everything's moving away from us, and then these redshifts are all slightly different. So he's saying that the H alpha line, which is the first line in the hydrogen series of spectrum, is redshifted, and the other ones aren't. But that's the spectroscopists are probably studying that, or have studied that.
The early papers, when they were looking at the redshifts of Sirius B, they started seeing that, the hydrogen alpha line has this redshift, and then the beta line has a different redshift, but the gamma line has a different redshift. And so they didn't agree with each other. And then now the metallic lines don't agree. So you just pick the one that you wanted, and I mean, it's just the whole thing is a mess. Well, none of this agrees.
I love something, Jen, that you said a while ago, which is that we're going into this era of AI, where right now we have the mapping of simple concepts, like words and like single symbols to other symbols. And at some point, we ought to be able to produce a system that actually maps concepts to one another, that allows you to massively increase our computational ability to verify how these systems, how these paradigms, and how these different perspectives on the same thing actually align or don't align. And I think that that's going to be really powerful for science in a way that the systems that we have right now might be less powerful.
Yeah. So it goes to abstraction. So humans think in something I call linear narrative. I see a dog, it's running here, and even equations, most proofs look like this linear set of equations. And since we can't really, we're talking about a white dwarf, which is, some unbelievable number of atoms, unbelievable distance apart, with some amazing number of actual observations, right? So, the solution to that should have been, let's say, 1 million equations with tens of thousands of parameters measured over years. That would be a proper data set. But a human can't do that. They can't do 1 million equations. We can do 10 at a time. And we can't do equations with too many terms. We love to collapse, right? And we can't take into all the... So
even 10 partial differential equations will have no generalizable solution.
Right, yeah. So now imagine a system that could actually solve, 1 million equations with thousands of parameters and over time. And when you were working on the science, it was always sort of calculating the best fit of that. And then you get some error signal. The error signal you just talked about of looking at the hydrogen alpha line, the error signal and everything else was 100%. Right. And you almost couldn't express the idea of just picking this one thing, because if a properly designed system said take into account everything you possibly can, throwing out a lot of stuff would just be crazy. And it might also help the subtractive problem in particle physics, where the sensors have to get really narrow. Well, if you could actually have lots of wide-ranging sensors, right, even for complex phenomena, and still get a useful signal out of it.
That's what a lot of scientists are doing. They're making the computer programs so they can figure out all those multiple calculations at once.
Then you might partially solve the subtractive engineering problem.
But what's here, I know so little about AI compared to you. I mean, I'm just a very much of a rookie. But my problem that I have, I'm scared that it'll just build on error. We're feeding these computers human acquired knowledge, And the computers, when you ask AI a question about the sun, or with ChatGPT, Hunziker did that. He had an episode where he asked ChatGPT about the sun and started arguing with ChatGPT. He's an interesting guy to do that. But my question is, how do we get the foundations right that you were talking about earlier in the episode? We don't quite have our foundations right, and the computer's not going to be able to give them to us, right? They have to start somewhere. Well, they start from human knowledge, right?
Yeah, well, they do currently. And this is a Jim's thesis.
Okay, Jim's thesis, okay.
Feeding language to AI models was a shortcut to seeming intelligence.
Okay.
Right. It's not, and then people say we're already giving it everything we can and we're reaching the limit. Right. So just look around this room, right? Like the color of that little spot is actually dependent on almost everything here. Right. And if I went in there and I made that spot a slightly different color, it would look wrong, because it would in fact be wrong. Right. So physical reality is solving for actual things. Right. And the only way that thing can be exactly the right color is if the laws are working everywhere. And if it was slightly different color, you would see it. Right. So already AI models, if you give it all things humans said and you lie about some facts, let's say you feed it, 1 trillion sentences, but you put in 20 lies, right? They'll stick out. Because they're not consistent with everything else. Okay. Right? But they're still human generated. And maybe the whole corpus of human thinking has a bias because how we think. Now, if you start building models that also have a lot of data gathered in a way that it's only consistent. So now the human thinking and the data from physics.
In terms of the sun, electricity is important. And when we talk to people that are astrophysicists and cosmologists, currents are electricity is not a major factor of how they model really anything.
Right. They don't think about currents, or they also don't think about chemistry, really.
Exactly.
There is astrochemistry, but they really have very limited stuff on the sun. They try to explain just the reactions that they know that if they have calcium hydride, they know somehow I got to mix the calcium with hydrogen and get that calcium hydride. But they don't really try to think beyond that in terms of condensation reactions on the sun. That's a big difference.
And so earlier you said that the reason that it looks like the corona is at millions of degrees is because you have this, is it fair to call it electrochemistry in the corona?
Yeah, that's what's happening.
Okay, so let's talk about that. Like, why is that important?
First, we know that the corona has a continuous spectrum. Now, for the astronomers, the way that they try to justify the spectrum of the corona is they say, well, wait, it's actually a photospheric spectrum that has been scattered by relativistic electrons that are causing us to have this continuous spectrum in the corona, okay? Because they don't have condensed matter there, so how do they get a continuous spectrum, right? So they just scatter the photospheric spectrum, and then by scattering it, they can get rid of the Fraunhofer lines, because the photospheric spectrum, if the surface of the sun is emitting a black body, above it there's atoms that are absorbing that radiation, and that gives us the Fraunhofer lines, which are superimposed on that spectrum. So, and also, in order for them to get that black body spectrum in the first place, since they're in a gas, how do they get it? So I had said that we'll get to the electricity eventually, but just did it so that people are clear. I had said that, look, to get a black body spectrum, you need the vibration of nuclei within.
The reason why electricity is not really considered, it is, there's no current that we've measured in space, so that's why there's no, electricity is not considered in some aspects, but the sun is made out of a plasma, which is not quite a gas. It's where the protons and electrons are separated, but they have to stay. They kind of stay within a certain distance. They're not the electrons are not orbiting the protons, so there is free electrons, and free electrons when they move create a magnetic field. And that's electricity, the movement of electrical particles. So there is some electromagnetic theory that does go into the sun, but it's not the primary source of energy in the sun. The primary source is nuclear fusion in the core.
A lattice structure. They don't have that in a gas model. So what they do is they, in the sun, for instance, they say, well, most of the continuous spectrum is coming from the negative hydrogen ion, which is hydrogen with 2 electrons on it. And that's highly unstable. I mean, it should not be present at all. And the problem is that if you look at the main sequence of the stars, the temperature changes along the main sequence. So as you go to O-class stars, you still get the continuous spectrum. But now you can't use that negative hydrogen ion to explain it. So now they have to have a different agency to explain that spectrum. So how do they get the spectrum on the sun? Now, it was Wilt and Chandrasekhar that said that you had negative hydrogen ion in the at the level of the photosphere, which is causing the continuous spectrum. But that's not sufficient. They need other processes. So that's what the Stellar Opacity Project was. I think it was at Los Alamos, where they took a whole bunch of processes that had nothing to do with thermal radiation, and then they just sum them together and say, oh, with all these processes summed, we can get a black body spectrum. But the problem is, none of those individual processes occurred at the same temperatures, right? They're looking at transitions, like bound transitions within atoms or something like that, and then they're putting them all together to give me this soup, which eventually gives the black body spectrum. And what I say is, no, the sun has to be like, it has to behave like we get a black body spectrum on Earth. It has to be done instantly, not by the summation of all these processes that are unrelated. So you get this black body spectrum from the surface of the sun, which in...
Okay, this is just speculation on my part. The reason why they can probably do that is why they can say there's multiple processes going on is because there's different energy levels at different levels of the sun, because there's different pressures and temperatures. So there's the further out you get lower pressure. So that's probably why they figured it out, and that's just a speculation on my part.
Which will come eventually. Science will move to a condensed matter to explain this. But there's neutral atoms above the surface of the sun, and they absorb some of that black body radiation. So that's why you get the Fraunhofer spectrum of the sun. Now in the corona, well, they don't have all these processes to build the continuous spectrum. They see it, but now they don't have, the negative hydrogen ion and all the things, all the suit that they had internally to the sun to give the continuous spectrum. So what they say is, oh, well, the way we get that spectrum is by taking the continuous spectrum of the sun with the Fraunhofer lines, but now we have relativistic electrons, and those relativistic electrons are scattering the spectrum and getting rid of the Fraunhofer lines, most of the Fraunhofer lines, and that's now why we have the coronal spectrum, which is continuous, but it's not really a property of the corona. It's a property of the photosphere. I mean, this is just the height of absurdity.
Fairly intelligent scattering, because it's scattering things in just the right amount to give you the spectrum and the other thing. And it's just Occam's razor says it's
it's just so what I'm saying is that there was at the eclipse of 1869, I think, in Iowa. It's a long time ago, and I can't remember the name of the man who said it in the paper, but he said that the corona was self-luminous. In 1869, somebody said it was self-luminous. He saw the continuous spectrum and he said it's self-luminous. Okay, but astronomy moved away from being self-luminous, right? They're now scattering photospheric light, and I'm saying no, it is self-luminous. You see the streamers in the corona; we have structure there. Okay, it's not relativistic electrons; it's self-luminous, and what's more, the coronal spectrum reddens as you move away from the surface, so it's cooling. Well, this shouldn't be happening if you're just scattering the light of the photosphere, right?
That is why we have the Parker Solar Probe in making measurements of the solar atmosphere. It's there to measure things and to try to give more data for scientists to figure out what's going on there.
Why is the spectrum of the sun reddening as you move away from the surface? So this speaks to the temperature. The temperature is lower as you move away, okay? But the current theory says we're at millions of degrees. And this gets back to now electrochemistry. Why are we getting millions of degrees? And what I'm saying is you have in the corona, you have condensed material, and it's linked all the way down to the surface of the sun. So you can see that actually, if you take an iron 13 spectrum of the sun, you'll see that iron 13 there's iron 13 very close to the center, to the sun, to the surface, and all the way out in the corona, right? You can see the iron 13 all the way, right? So what's happening is you have charged material.
What iron 13 is iron that's been stripped of 13 electrons. If you have iron 23, it's stripped of 23 electrons, and there it goes up to iron 26. To strip off the electrons, you have to give it energy to do so. He thinks it's some electrochemistry in the sun. A lot of theories are focused on it being the sun, somehow the sun's heating it up. Some of its magnetic fields causing it to be moved at a faster and faster, and they collide and they lose the outer electrons. And that's the modern theory to it.
Material. It's electropositive. So the corona.
If it's labeled SpaceX, I'm sorry, I messed things up.
It's plasma, it's mostly plasma, but there is some condensed matter. And what that condensed matter is doing is it's electropositive, and it's bringing charge from the outside of the corona. If you have a neutral atom like iron, it now touches this highly electropositive material, and then it loses its electrons, and the electrons are now channeled back to the surface of the sun. And when this becomes equivalent to a condensation reaction, there's going to be heat involved. And to get rid of the heat, the iron promotes one of its remaining electron, and then that emits light, and that gets rid of the heat. So that's the emission line that we see as a sign of a condensation process. So that's why the lines are emitting. They're giving away their electrons and they're emitting light.
Why is there this electropositive material there?
Why is it there?
Yeah.
I'm not sure why it is that it's there, but if you look at the formation of how would we form a star, in one of the ways you could form a star is with hydrogen clusters. And so so in the modern theory of the sun, you eventually get to your question, but we'll start at why could the sun naturally be positive, have positive charge? So in the modern theory of solar formation, you have a cloud and it self-gravitates. That's the modern theory, right? In the standard model of the sun, you have
that's not quite right. There is a cloud, but what happens is there's a shock wave from a supernova, or there's a shock wave from like a massive star, and the solar winds pushing material one way and maybe something going the other way. In the galactic arms, if you look at spiral galaxies, you see these spiral-shaped arms, and what happens there is a lot of matter just ends up colliding with one another and just can start forming stars, but it's not just the self-collapsing cloud. It doesn't do that.
A nebular cloud, and it self-gravitates and forms a star. It's kind of like the hands of God came and pushed this gas together, right? But the problem is that gases don't self-compress. Okay, that doesn't happen. And when you cause a gas to gravitationally collapse, like they require in astronomy, and I was telling this to Jim yesterday, you actually generate negative heat capacity. So that the gas will, as it loses light, as it emits light, it actually becomes hotter. So the temperature goes up as it emits photons. So it's got negative heat capacity. Whereas normally a gas has positive capacity. If it emits light, it cools. So what's happening is that all gases.
Sorry, I didn't follow. Is that some feature of compression, or like why is that?
No, it's because their models are wrong. Gases. So gases. All gases that we have on Earth, they all have positive heat capacity. But in astronomy, because they caused the gas to self-gravitate, when they did that, they made the heat capacity negative. They got it in their mathematics. The heat capacity became negative, and they said, oh yeah, stars will actually heat as they age. So Eddington actually writes in his book, I don't know how we're going to get out of this. How are we going to get out of this vicious cycle that as the star starts condensing on itself, okay, the temperature is going to go up as it's radiating away heat. How are we going to get out of this? And what ends up happening is they solve it with a Nobel Prize. They give a Nobel Prize to Chandrasekhar for degenerate matter, right? So what happens is the star compresses itself, and eventually you get a degenerate object, and that stops the compression. So that's why they want the white dwarf.
Degenerate matter is... The thing is, matter has... What we consider matter has a spin, like protons have a spin and electrons have a spin. And only two objects with the same energy level can occupy a certain energy. This could become complicated. Like electrons have orbitals, and only two electrons can be in one of those orbitals. One has a upspin, one has a downspin. Degenerate matter is when those laws kind of break down and gravity kind of pushes things together. When you have a neutron star, it pushes on the surface, it pushes the electrons into protons and creates a neutron star. That's what, and so it's a quantum mechanical process. That's how it happens. I don't think it has anything to do with how stars form. When stars start contracting, they give off heat, and there's different phases of star formation. So it's one of those things you have to go into real detail to figure out. But he knows best.
Theory, because that also solves their negative heat capacity for the sun. So all these things are related problems. They're not independent. They created a monster, and then they solved it by giving us degenerate matter in the stars.
And it's also observationally contraindicated, right? Because these giant nebular clouds are actually not gravitationally bound, and increasingly evident that that's not the case.
Right. And that's correct. They actually have seen expansions in some of these clouds, so it's not working. So gases expand. They expand to fill the void, and so this just doesn't work, and that's their mathematics doesn't work. So what happens? So if it's not gravitational collapse, how do you build a star? So the idea
but it's fairly easy to calculate. If you take a gas, right, and you say, all right, here's a gas that's like the mass of the sun and it's some big space, and then it has a temperature and energy. If you say, what's the odds of it collapsing? Well, the gravitational field of any piece of the gas falls off so fast, it doesn't counteract its natural tendency to disperse just by random thermal motion.
Right.
And it's not a hard calculation to make.
Right.
Like there's just nothing to it.
You can pop a huge balloon in space and it will...
Yeah. So then the counter theory is, there's a big gas, and something like a shock wave from a supernova causes some movement in the gas to sort of trigger the condensing event. But it's not obvious what
James Jeans went even further, right? In the idea that you make a star from gravitational collapse, James Jeans actually invoked that, I can't remember if it was photons or whatever coming out from the outside and then containing this thing and slowly making it into like a self-compression. But anyhow, so if it's not self-compression, what is it? So what I say is, if you look at cluster chemistry, and so I'm an organic chemist, you look at how does hydrogen actually, some people think, well, hydrogen is just diatomic. Two hydrogen atoms come together and that's it. It doesn't grow anymore. That's not correct. If you add a proton, you'll get H3+. And if you then you can add another, maybe a hydrogen atom to it, and it just keeps growing. Okay, and you can keep building, as long as you have positive charge with it, you can keep building larger and larger clusters. So we have clusters of hydrogen now that are more than 100 atoms together that's been built in the laboratory. And so what happens is that you get these hydrogens come together, and now you've delocalized the electrons within this cluster. That's how they're sticking together. You're starting to delocalize the electrons. They're starting to share electrons. So what I'm saying is a star actually starts by a very simple process, one atom at a time, that you have hydrogen, you have it coming together, and then there's a positive charge that comes. And so eventually you build up this cluster larger and larger, and in the end, it's positive. So then when you have a star, where are you going to put this positive charge? And what I'm saying is the positive charge is moved out into the corona. Okay, the star at the surface of the sun, we know that it's neutral. Above the granules, it's neutral. There's lots of neutrals there. That's also my argument against the negative hydrogen ion, by the way. Why don't we see fluoride or chloride? We don't see them. So if you don't see those, and we know there's hydrogen chloride in sunspots, we've seen it. So if there is chloride and fluoride, okay, hydrogen fluoride, you never see them as free ions. You only see the molecules. Okay, so if that's true, if you can't even see chloride or
The positive part is the nucleus, and we've pretty much figured out there's nuclear fusion in the core. So how can there be a positive charge on the outside if there's nuclear fusion going on the inside?
fluoride, how are you going to get hydrogen anion? Okay, so it just doesn't make sense.
Is there any hope of seeing these little droplets, these primordial starlets?
I don't know what is hope. I mean, they're pretty far away, and how are we going to detect them? Sometimes maybe by spectroscopy you could see them, but I don't know what the spectroscopic signature would look like. Maybe we've already seen it.
If we can already make in the lab clusters of 100,
right.
Is there a way to stimulate it with the ambient radiation of the galaxy and then see if it has absorption?
Yeah, well, maybe there is.
Like that's a nice.
Yeah, maybe there is. And this could be my ignorance of. Yeah. Somebody might be listening to the video and say, "Oh, well, here's a spectrum of H83, H83 plus or something like that. That it does exist, and that's a spectrum. I've never seen the spectrum, so I can't say what the spectrum would look like.
What induces hydrogen to start to bond in that way? Like if you have a gas
it's a sharing of charge, right? You've got a proton and it's looking for electrons, and it comes and just shares the electrons that are available. So it's all about delocalizing electrons over lots of atoms, and that's just how metallic hydrogen is. It's sharing its electrons. And also Neil Ashcroft, who had written to me, he was probably the top person in the theory of metallic hydrogen in this country. And when I wrote the 40 proofs paper, and I talked about this in a previous video, but when I wrote the 40 proofs paper, people were upset because I emailed the scientists of the world. Like I got a list of all the world's physics departments, and then my sons and a whole bunch of people got together and we emailed like 70,000 people.
That's incredible.
Here's the 40 proofs paper. So physicists cannot say that they don't know about the 40 proofs paper because I emailed it to 70,000 physicists around the world.
Check your inbox.
I check my inbox. I check their inbox. And of course I've been attacked for this, but John Wilkins, who is like one of the best physicists in the country, he actually said, I said, I'm thinking, when I first I did it for two papers, the WMAP paper, WMAP radiological analysis, and the 40 proofs paper. And when I did the WMAP
I'm sorry for putting people through this if you're actually watching, but I'm kind of tired of flat Earth most nights, and making fun of Mikey. But if anybody finds this interesting, please hit the like.
Biological analysis paper. John was he'd come over for Thanksgiving and Christmas. So that Thanksgiving we were emailing the WMAP paper around the world. It also got over 60,000 deliveries to physics departments around the world. And so I asked John what he thought, and he goes, "Well, I guess there's nothing wrong with sending a polite email." And you should know that Raman, who had won the Nobel Prize for Raman spectroscopy, when he discovered Raman spectroscopy, he got a secretary to send letters around the world of the discovery. And then some Russians got his letter. They were working on the same experiment, but they saw that Raman had just finished publishing it. Okay, so it is okay. Now people didn't like my methods, but here's what John said, right? I guess it's okay to send a brief email, to everyone. So that Monday, so that was Thanksgiving. John goes to work on Monday, and an astronomer that knows him well, he was furious and I had just finished emailing with you, and he was just furious to get the WMAP paper and talk to John about it. That Robitaille sent me this WMAP paper and blah blah blah. And John just goes to him. He said, John told me what he told me. He said, "Well, did you read it? Did you take the time to read it?" And so the WMAP paper, some people did clearly read it. I got a lot of response back. And the 40 proofs paper, the same thing, was downloaded tens of thousands of times from the server of Progress in Physics, because Dimitri would keep the downloads and tell me, So I know they downloaded it. So anyhow, so now what was the question that caused me to talk about this? It was, why is it positive? So you can see that now it grew as a positive entity. And now what I'm saying, it's like a Van de Graaff. The sun has a corona, and it's sending those charges out away from the surface, and the surface is surrounded by neutrals. Okay, so I think everything fits that it's pushed now these charges out. Once it made metallic hydrogen, it pushed the charges out. And so we want to have it electron rich. The sun is more electron rich. It could be totally very close.
Okay, I'm going to skip ahead and do something here. I hope I get the right chapter.
Saturn?
They end up, what I say is the stars are moving, as they move down the main sequence, they're slowly cooling. So most stars are along the main sequence. So
this is one thing a lot of people who have alternate theories of astronomy don't get, is they think that a star starts off like an O-type star and goes down the main sequence of stars to a red dwarf K star. These stars evolve to go to they start from the mass of like an O-type star starts with a very massive cloud and condenses into an O-type star. There's a certain track called the Hayabusa track. Yes, I'm mispronouncing a lot of things, but there's a track for that to become an O-type star, and then once it's done an O-type star on the main sequence, it becomes a giant star, or supernovas. For a star like the sun, it starts with a cloud just larger than the sun, that goes on this track and becomes a G-type star. Like there's O, B, A, F, G, K, and M. And actually there's L and Y for brown dwarfs now. But they evolve from the dust cloud into each one of these types of stars. They don't go down the main sequence and cool off. I don't get where they get this idea from. But it's one thing most of them do.
That's what we want. We just want them to keep stay along the main sequence and just slowly cool and become a red dwarf.
If you stand that main sequence long enough, you actually can get to the spectrum of Jupiter.
Right. You get to objects that have very, very high molecular characteristics. They're very rich in molecules at the end of the main sequence when you get to M-class stars and so on. So they're cooling and then they're staying along the main sequence. And then you have unstable stars. So when I talk about the sun, I say, okay, it has intercalate zones inside of it, and when the intercalate zones expand, that explains why we get a red giant, right? That you get, it's like the piece of graphite that if you take a piece of graphite, and I mentioned this to Shiloh yesterday, if you take a piece of graphite and you put it on a table and it's 1 centimeter thick and you saturate it, you make it super saturated with a gas, and then you strike the table with a hammer, it'll expand 100-fold. So if a star has intercalate regions within it, so you have a hexagonal planar hydrogen layer, and then you have an intercalate region, well now if something comes and shocks that star, then that can cause the intercalate region to go from solid phase into gas phase, and the whole thing will explode either as a supernova.
The way we actually know what we actually know how this works is that there are different different materials. When they fuse, they give off different amounts of heat, and like right now the sun's burning hydrogen for the next 4.5 billion years, and then eventually it will burn helium, which is the byproduct of hydrogen burning, and that will give off more heat and it will expand. I have to do we'll have to do a deep dive into what he thinks these intercalates are, but it's basically impurities in the stars.
Or slowly explode and become a giant, and that could explain why stars are repeatedly going nova. There's several stars that have repeated nova.
That's what.
Yeah. So the intercalate zone. When I talk about this model of the sun, it's not just that it well explains the emission of the sun that we get.
There are many stars that pulse because their different energy levels happen. Cepheids are one. When they're transitioning to a giant star, there's like hydrogen. There's helium in the atmospheres, and the star will, on the way, shrink it down, and then all of a sudden you have this. There's enough helium concentrated near the core or in the atmosphere to give off enough heat, and then it'll expand, and it'll do this a lot. Stars going to the red giant stage will do this, which is another way of determining how far away an object is.
The thermal spectrum properly, but it explains other star types, because the intercalate region, once you form it, you can now automatically explain both red giants and supernova very elegantly without coming out with some new wild idea. These things fit into known inorganic chemistry.
So where are all these dead stars at?
What do you mean the dead stars?
So if they're cooling off the main sequence, Well,
I don't know how old the universe is.
Well, that's what I'm saying. So if the Big Bang turns out to be not 14 billion years ago.
Yeah, now we're at 26.
Okay, whatever we're up to, right? Let's say it keeps getting longer and longer. Let's not even say that the universe is eternal, but let's just say it was a long time ago, the birth of the universe. Shouldn't we have a huge zoo of Jupiter-ish looking dark stars?
Maybe we do have such objects, and we just can't detect them. They're so cool. I don't know if they're there or not. They'd be far away from our sun, so how do we detect them? So I'm not saying that they're absent. I don't know that there's evidence that they're present.
Or is it possible that they're right here with us and we just don't recognize them?
Right here.
But what do you mean by right here?
Well, like Jupiter or Saturn.
Oh no, I don't think that the stars. I think that Jupiter and Saturn, all our planets, because they're in the ecliptic, I think they were emitted from the sun.
It's funny because we talked to this astronomer at Bordeaux. So Sean does these simulations, and we kind of press him on this, because that is often the response is that, well, no, even if you had all the time in the world, sure, maybe these dead stars would look like Jupiter, but we couldn't get them in the ecliptic. And so he actually ran these simulations, and he determined that it actually was possible that a passing body like Jupiter could get captured into the ecliptic, but that it was extremely unlikely, right?
Well, the problem is, if you look at the distance to the nearest star.
But given something, I'm not going to say given eternity, I'm going to go with given a great deal of time.
But why do you want to capture the planet when you could just form it by ejecting it as the luminous blue variables do? Well, we have evidence that the luminous blue variables are ejecting material, and when you eject Jupiter, remember that most of the angular momentum of the solar system is in Jupiter and Saturn. So when the stars were made, they had high angular momentum, and how are they getting rid of that momentum, they eject the planets. So that also solves the angular momentum problem. Whereas capturing Jupiter and Saturn doesn't solve your angular momentum problem of the central star.
Makes it worse.
It makes it much worse. So now,
So they bring a lot of angular momentum to the table with their capture.
no, but the problem is that it's thought that stars. So in modern theory, when you form a star through this gravitational collapse, they try to figure out how are we going to get rid of the angular momentum, and they do that with solar winds or magnetic fields to try to get rid of the angular momentum of the central star. Now in this model, I'm getting rid of the angular momentum very nicely by ejecting the planets in the ecliptic plane from the central star.
I think you just predicted the mass of the planets in a stellar system, right? Because if you know the mass of the star, and you think you know its rotation rate, then you know the mass of the planets there. That slowed it. You know what the angular momentum of the star would have been.
Well, we know that the sun currently has about 4%. So it depends how you calculate it. If the sun is homogeneous throughout, it has about 4% of the angular momentum of the solar system. But most of the angular momentum is sitting in Jupiter. I think it's got about 60% of the angular momentum of the solar system.
Something that I haven't totally understood.
Of course, that one's orbital and the other one is spinning.
Okay, that's what I was going to ask.
Okay, so the axis is really big.
Yeah.
It's like the old force time.
So for Jupiter, we're talking about orbital angular momentum. So we had spin angular momentum, and it was converted into orbital angular momentum in the planets.
Got it.
Okay, but if you look at the total angular momentum of the solar system, the sun is about 4% if you assume that the sun is relatively homogeneous. If you assume the standard model of the sun, where they put all the mass at the center, most of the mass at the center, because they have a very high density at the center, then it's only about 0.3% of the angular momentum of the solar system.
Wow.
But so what I'm saying about this new model is it does enable us to account, because I'm looking at how were the stars formed. When we started making a lattice, the luminous blue variable became unstable, right? And so it emitted the initial lattice. As it cooled, it's starting to form a lattice, and it's emitting them as planets. And then after that, it cools itself more and more. As it loses angular momentum, it doesn't have the ability to kick out more material. So the star, our sun, as it started forming a lattice, it initially gets rid of a lot of its angular momentum with the gas giants, and it cools more and more, and then it has less angular momentum to get rid of. But now it does it with more evolved planets, which are the central planets. The sun is making those elements more and more complex, and now the central planet, like our planet, has much more evolved atoms on it. So I think it fits very nicely. But of course, people can criticize the idea. Think about it.
Do you think like the Earth and Venus were ejected as is, or do you think they were more of a gassy ball, but they're close enough to the sun that subsequent mini eruptions blew the gas off?
So I don't have all the explanations of how they were emitted in terms of time, but it's likely that the Earth and the Moon could have been emitted simultaneously. They're very close in time. So essentially simultaneously, so that it's not something that came and hit the Earth and made the Moon, and that they came out simultaneously.
That seems like a justice story.
There's some really interesting movements in planetary science right now concerning the evolution of Neptune's two super Earth-like planets, and of course the Earth being a smaller version of something like that. And so I do see people in that field starting to entertain the idea that planets evolve from one sort into another, given proper conditions. And of course, you can accelerate that by moving the giant closer to the star and rapidly photo-evaporating its surface and things like this. But it seems like it's at least a potential solution to the distribution of these planets inside of a lot of these exoplanetary systems that we're observing.
Well, I don't know that there are a bunch of exoplanetary systems, by the way. So remember that how are they detecting all these exoplanets? I mean,
differently.
There's several ways, but one of the most prominent ways is always a change in luminosity of the central star. They don't see the planet; they just see that the central star is oscillating in its luminosity. And I'm saying no, that oscillation is coming because the star is oscillating between one lattice type and another, and so it changes its luminosity. So there's actually no planet. That's why you get these, to me, absurd numbers where you get a planet or two stars orbiting one another in 4 hours, or a few hours for a planet to go around the sun, around its central star. And what is more likely to happen is that you have a phenomenon going on the surface of the star where it's oscillating between one lattice type and another. So it's on the phase diagram that you have pressure on one axis and temperature on the other, and you're just moving up and down.
Scientists actually make papers where they actually study the chances of there being something on the star, like a sunspot or a solar flare or something going on the sun. There's a number of papers written. I actually years ago found a paper by one of the co-authors was a guy that I went to university with, who studied this. So they actually do study the chances of these planets not being planets, but other phenomena on the star. So that's one thing that's going on. No, the planets do not get ejected. That we have observations of stars being stars forming planets in dark dust rings around the stars. So, and there's a logical fallacy called the logical fallacy of incredulity, which means if I don't understand it, it does not exist. And Robitaille does this greatly. Okay, I'm going to let him talk again. But
down along a line where the temperature is changing, but the pressures aren't changing. But when you go from one temperature to another, you're changing lattice, and that changes the emissivity. So now we get back to this point of emissivity not being present in the seven.
Boy, we were real done at a party recently because people kept coming up to us and asking us what we thought about the discovery of life on this exoplanet. And your video, or I don't know if it was a conversation or a video I watched of you, but your idea was fresh in our mind, and we had to be like, well, they might not have even seen a planet at all.
Well, I love when they discover planets. They always have a really good picture.
Oh, yeah.
It's like the same resolution as the picture of Jupiter, which is amazing. And
And all these exoplanets are all large. They're all Jupiter-sized planets because they need that, because remember, they need to call it a star. So they have to have a pretty big planet going.
Actually, a lot of the newer star planets are more Earth-size. I think about 2.5 or 2 times the size of the radius of the Earth, because we developed better techniques and better instruments to detect them. So, them all being gas giants is not true.
Going around, it's overreach. Now that it's overreach when you look at the luminosity of the star. Now there's another way to detect planets, and that's looking at the spectra. You're looking at spectra, and that's more complicated, and I have to look at it more carefully and see, okay, are we actually seeing a planet? Because remember that the spectra of a star can change as well. If you change the underlying crystal structure of the photosphere itself, that could affect what you're seeing above that photosphere, because these things are linked.
Well, there's a few that we see from the top down, right?
There's some that we see visual. There's actual visual observation of exoplanets, and they move slowly. I mean, it takes years for the planet to go around the star.
These ones are found further away from the star, and because if they were found closer to the star, the star's light would overpower them. So that's why they're found further out. It doesn't mean that they're the only planets being formed or being seen.
These are not spinning tremendously fast, and so the exoplanets that we've seen optically, those are moving slowly, like we expect.
Because the plane is perpendicular to us.
Yeah,
and then they just see them.
And we see the planet rotating.
Like I've seen photo or images where it's the protostellar disk, or like the sun still has like a large disk, and there's lines that are etched into it. Also.
Now you hit a sore point for me. So this is an example.
Filter refinement.
So this is the problem with astronomy, right? They want to see protoplanet. They want to see a protoplanetary disk.
That's right, yeah.
Okay, so they see a disk around a star and they say that's protoplanetary. Well, how do they know it's protoplanetary? It could be that the star ejected that disk.
Well, it's got lines in it.
It's got lines in it. That's fine, but it doesn't mean that it's part of how the planets were made.
Yeah.
The star could have just created this disk itself by ejecting material from its equator and into its ecliptic plane. So my problem is, if you look at our own solar system, right? We have an asteroid belt between Mars and Jupiter, and I talked about this 2 weeks ago. There was a person at the Naval Observatory. He's deceased now. His name was Tom Van Flandern. And Tom, the one thing I'll say about him is he had the most beautiful blue eyes I can remember. But Tom, he was.
So sweet.
I just will always remember this man's blue eyes. He had great blue eyes. And so Tom believed that the asteroid belt came because a planet was once there. Because if you look at the Titus-Bode law, the planets occur. According to this law, we know all the way out to Uranus that they follow the Titus-Bode law for the distribution of the planets. And right where Sirius is, which is an asteroid in the asteroid belt, that's the proper position for a planet to have once existed. And Tom Van Flandern actually stated that there was a planet there once, and it exploded, and that created the asteroid belt. And most of the material of the planet is now gone. Now, even the astronomers say that 99% of the material that was once in the asteroid belt is now gone. Okay, that's their own belief.
What probably happened was the gravitational pull from Jupiter and Mars. Mars is kind of at the edge of the asteroid belt. Probably disturbed the formation of any planet that was there, or any material that could be in a planet. And yes, a lot of it probably has ejected out to like the Oort cloud or further out into space. Oumuamua and Borisov, which are the first 2 known extrastellar objects, probably were objects in another solar system that got ejected out into space from one of these belts.
So why do we have an asteroid belt there if the planets are formed by protoplanetary mechanisms? I mean, why isn't the asteroid belt accreting all its matter and forming a planet? It doesn't. It never will. Because when they treat the angular momentum of the solar system, they treat it as solid body rotation. Well, a solid body rotation, how is this piece of material going to catch the piece in front of it if they're both rotating as solid bodies? It doesn't work. And actually, Steve right now is writing a paper against all this accretion stuff in astronomy, that there's violations of thermodynamics right and left in the accretion mathematics, that they make temperature non-intensive and so on. So there's some real problems there.
You can't get pebbles to stick together either, it turns out. Yeah, so you can get grains of sand to stick together, but pebbles just bounce off each other.
Well, then some of the asteroids are so cool because it looks like there's 2 balls stuck together. And the shapes are really complicated.
Okay. So anyhow,
I don't think there's explanations for that.
Well, there's another problem too. Some of those asteroids like Ceres you mentioned in Vesta, they're too rounded to actually be in this hydrodynamic equilibrium necessary to round a body out. Like we were talking about, the sun is almost perfectly round, and they have this hydrodynamic explanation for why that's the case. But you can't actually apply that to some of these asteroids. You don't have enough mass to pull it off. And so, well, how did they get so round? Could they have been...
They bump into each other.
Like a rock tumbler?
It's a rock tumbler. It's an asteroid rock tumbler.
Okay.
I think that rock tumblers get you smooth, but I don't necessarily know that they get you round. Do they? I guess maybe long.
Okay. Most grains that start forming planets and stars are actually about the size of a millimeter. And what they are is like a silicone or metal on the inside, and on the outside there's an icy shell. And these things, when they collide together, they start warming up and they start melting and fuse together. And that's how a lot of these, and they just start fusing together, and the outside becomes a frozen shell, and then you get some rock in the middle. And they eventually grow and grow and grow into bigger and bigger objects. So it's not a rock, not like rock like we think of it. It's just these little pieces of dust coated with ice that form planets and stars at the beginning. And so ice is a lot easier to melt and a lot easier for it to stick together. Okay, let's get back to them.
Long enough. River rocks are very round.
Yeah, they're kind of rounded.
Over long enough time.
It's probably a number of processes, probably gravitational forces and things colliding that creates round shapes. But after a certain size, there is just gravitational energy that does it.
It's kind of wild. Well, river rocks are another mystery. Like, what are the river rocks doing at the top of mountains?
That's one of my favorite things.
It's really fun. Well, but on the observation, you pointed out that the black hole picture was 6 pixels at 100 megahertz. Oh, you pointed that out. And then somebody said it's amazing that the picture looked just like the black hole in Interstellar, which is hilarious because they asked the physicists what it should look like, and then they made an image, and then they recreated the black hole that looked like. And
that image was just disaster. I mean, they had like 5 points, and they took a Fourier transform on 5 points. It's like, okay, only in your mind.
Okay. They took more than 5 points. Well, if you saw the amount of hard drives that they used, so they did it over a number of times, and they took observations from around the world to make that black hole image. Okay, I'm going to call it quits. My voice is about to give out. I don't normally talk this long. So I hope everybody has a good day, and goodbye. Mm-hmm.